Hello. So in this review session, the plan is to go over the practice final that he posted. Are there any questions you guys want to go over first, or any topics you guys want to go over first for this review session? NMR. Okay. So HNMR, for this type of problem here, or in general, everything in general about HNMR. Oh, identify the molecule. Okay. So let's work on
I
this
don't know. I
NMR.
can't relate to any of this. I don't. We don't do that really.
Oh, he said you don't have to worry about this for the final. This one here. Yeah. So for the IR, there was this graph that I like to use for finding the presence of functional
Ain't
groups.
it cool?
So that's the one.
Come home. I came home bloody.
Okay. Okay. So I'm trying to find that chart right now. Let's see, what was it? It's this one. Yeah, this one. Right. So this IR graph would help you determine what kind of functional groups are present in the molecule that you're trying to figure out. Right. And for HNMR, there are ranges of the ppm that you have to be familiar with, which this is a good chart for it. But I could go over this in more detail when I import this into here. Yeah, so this HNMR IR stuff is a lot of practice and trial and error, like a lot of guessing at first, and then if it doesn't work, you try again, and then see it, if it matches up with the let's say HNMR is very specific. You have to worry about the n+1 rule, the integration, how many hydrogens are represented in each peak, the de-shielded versus shielded peaks, right? Where n is going to be representing the number of neighbors, right? Does he tell you to draw out the molecule giving the HNMR graph and IR, or does he give you the IR and NMR already, and then you have to determine what structure you have? Right. Okay. 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 Well, let's right here. So let's go over the HNMR here. If you see anything to the right of it, the right region, this is called the shielded region, right? Anything to the left of it is going to be called the de-shielded region, right? So what this will mean is that this HNMR will shine a magnet to an atom that has a lot of hydrogens on it, right? HNMR will read the hydrogen atoms in the molecule, right? So let's say there are electrons floating around the hydrogen right there, right? And let's say that hydrogen is bonded to a non-electronegative atom like carbon, right? This carbon atom here is not electronegative enough to withdraw electrons or pull electrons to the hydrogen, which is why this is considered shielded. This hydrogen here is shielded by the electrons, right? But if we attach this hydrogen to some kind of electronegative atom like oxygen, fluorine, chlorine, that atom is electronegative enough for the withdrawal of electrons, right? So this hydrogen here will have less electrons around it because this electronegative atom here is going to pull on those electrons on the hydrogen, right? Which is why this hydrogen is considered d-shielded. It has less electrons shielding that hydrogen right there, right? And we see here the d-shielded regions are the hydrogens on atoms that are like electronegative, right? Are you guys familiar with the peaks here, or do you guys want me to go over like what peak represents here? Right. Yeah, so let's go over this. I'll go over it and how I like to think about it. Right. So let's say 0 to let's say around 2 is your boring carbon hydrogen bond, right? No other electronegative atom nearby attached to it, right? It's just a non-polar bond between carbon and hydrogen. Between 2 to, let's say, 3 is going to be your alpha region, right? And this hydrogen here is going to be alpha to, let's say, oh, no, not that. A double bond, right? So this is an alkene right here. Alpha to the alkene is 1 carbon away from that alkene, right? So this is the alpha carbon. This alpha carbon here is attached to a hydrogen. So this is considered the alpha hydrogen. It doesn't have to be an alkene. It could be a carbonyl, a carbon double bond oxygen like that, right? Where this is the alpha carbon that is attached to this carbonyl here, 1 carbon away from the carbonyl, right? It could also come from an alkyne, a triple bond, right? So let's say this is the alpha carbon right here, 1 attached, 1 away from the alkyne right there, right? That's the alpha carbon. This is considered the alpha hydrogen. And it doesn't have to be alpha to alkyne. It could be a terminal alkyne hydrogen, right? Where we notice that this hydrogen here is part of the alkyne itself. It's not alpha, it's directly attached to that sp carbon right there, right? So that's the 2 to 3 region here. And then once we move on to like around 3 to 4, that's when the hydrogen is attached to some kind of electronegative atom, right? Where X could be oxygen, nitrogen, fluorine, bromine, chlorine, iodine, right? The electronegative atoms. Because it's going to become more de-shielded as the electrons of hydrogens are being withdrawn, right? Now between 4 to 6 is going to be your alkene hydrogens, right? So let's say we have this alkene right here. These hydrogens directly attached to the alkene or the alkene hydrogens, which is going to be shown around 4 to 6. Right? This is different than the alpha carbon to the alkene, right? This hydrogen right here at the 2 to 3 range is not directly attached to the alkene. It's attached to the alpha carbon, which is 1 carbon away from the alkene, right? Now, 6 to, let's say, around 9, these are your aromatic hydrogens, benzene hydrogens. Right, so if you see benzene ring, if you see hydrogen directly attached to that carbon, then that's going to show up between 6 to 9. And you'll learn more about the patterns of this in the beginning of 118D, the benzene, right? Especially in the lab. But you'll learn about this in the middle of 118B, the types of reactions they could do. Right? Now, between 9 to 10, now this gets like more like clearer to see. Like the separation is much more clear. 9 to 10 is your aldehyde hydrogen, right? And then 10 to, let's say, 14, 12 to 14. Let's say 13. 10 to 13 is your carboxylic acid hydrogen. Right. Oh, there is another thing that I wanted to go over. Between 0.5, right? 0.5 and 4 are going to be your alcohol or amine bond. right? Because this hydrogen here that is directly attached to that electronegative atom, oxygen or nitrogen, is going to be able to do H bonds. Since that hydrogen is going to be partial positive, this electronegative atom is going to be partially negative, and it's not going to show up as a sharp peak like you're used to, right? Like most of the peaks here will be sharp, and there could be some peaks like that to represent how many neighbors they have from the n+1 row, right? But if you see an alcohol or nitrogen or an amine 0 to 4, you're going to see that as a broad peak like that, right? And this broad peak comes from the H bond between the hydrogen and the electronegative atom, right? So these are the things I look for in H&MR, the functional groups. Yeah, like more shielded to the right, more de-shielded to the left. Any questions on that so far? And then we'll see that on the practice final. I haven't looked at the practice final yet, but we could go over that. Yeah. But let's see if it matches up with this. Yep, the regular thing, alpha region, electronegative atom, alkene, benzene, aldehyde, carboxylic acid. Okay, so let's look at practice problem here to see what kind of questions he's looking for. What kind of answers? Let's see. Okay, so please match the molecules in this reaction to H&MR from the 4 different picture below. Note that one of the 4 picture below is unrelated to any of these 3 compounds. 1, 2, 3. Numbers above each peak in the spectrum represents the integration of the peak, right? So integration, let's go over that concept. It's going to be the number of hydrogens in a set or a peak, right? So the hydrogen on OH frequently gives no signal on H&MR, right? So the hydrogen on OH, they tend to give no sharp signal on H&MR, but they do give a broad peak at around 0.5 to 4 ppm. Let's see if he includes that in his H&MR. Oh, yeah, he does not. Let's see. Okay. So, what is this hydrogen? What do we predict that hydrogen to be a part of? Like what region? Let me copy and paste the HMR graph I drew earlier up there. Let's say copy. Let's say it's right here. Right. So given this H&MR thing right here, what range will this hydrogen attached to the terminal alkyne be part of? Yeah, 2 to 3, because that's the alpha region where we see hydrogen directly attached to the alkyne. So let's look at that range here, 2 to 3. Right. Let me label this 3, 3, 3, 3. Okay. Right. So we see here that from the options A, B, C, D, B has nothing between 2 to 3, so we could eliminate that for the first molecule. We could do the same for C, because there's nothing there between 2 to 3. And now for option D right here, there is something there between 2 to 3, right? But notice the number of subpeaks here. There's 1, 2, 3, 4, 5 subpeaks, meaning that it will have four neighbors, right? That one specific peak right there, four neighbors, right? And this number on the top right here is the integration, meaning that that's the amount of hydrogens representing this peak right here. So this peak right here could represent, let's say, these two hydrogens right here with four neighbors, which could look like this right here, right? 1, 2, 3, 4 neighbors. And to count the number of neighbors, start at one of the hydrogens in the peak, and then if you go 3 bonds away, you should land on another hydrogen. So let's go 1, 2, 3. That lands on hydrogen. That's considered a neighbor, right? 1, 2, 3, neighbor. 1, 2, 3, neighbor. 1, 2, 3, neighbor. Right. So that's the number of neighbors right there. Right. But if we look at the structure of A right here, if we go from this hydrogen, 1, 2, 3, that's a carbon. That carbon would not count as a neighbor. So that's why for, where is it? This one here, this integration of 1 is going to represent that hydrogen that we have. So I'm going to say that this is going to go with A, right? Where this one hydrogen here, I'm going to label these hydrogens, let's say H, 1, 2, 3, 1, 2, 3. This is a peak, let's say A, peak B, peak C, right? Since I labeled that C, this is going to be C right here, right? There's only one hydrogen of set C, which is that one terminal alkyne hydrogen right there. And we see that it is a singlet meaning that it will have 0 neighbors. And has 0 neighbors because if we go here and we go 3 away, 1, 2, 3, it lands on a carbon. That carbon does not count as a neighbor, right? Now we could see that B is going to represent this peak right here, right? Because the B hydrogens, there's 2 of them, which represents like which this number represents the integration of 2 hydrogens, which are these 2 hydrogens here, right? And we see that it has 1, 2, 3, 4 subpeaks, which means that it will have 3 neighbors, right? And its 3 neighbors are these 3 hydrogens here. So to make sure that those are the 3 neighbors, we start with 1, we go 3 away. 1, 2, 3, that's a neighbor. 1, 2, 3, that's a neighbor. 1, 2, 3, that's a neighbor. So that checks out, right? So that means that this right here is going to be C, right? Because, wait, no, we didn't use C. It's A, right? Because there are 3 hydrogens in set A, which are these 3 hydrogens here, right? And we see that it has 1, 2, 3 subpeaks, which is going to represent 2 neighbors, right? Which are these 2 neighbors right here. So let's make sure starting from this hydrogen here, we go 1, 2, 3, right? 1, 2, 3. And another way to verify this is that notice at peak B, right? This peak B is between 2 to 3, which we said was the alpha region. And that makes sense because this carbon right here is alpha to the alkyne right here, right? This is the alkyne, this is the alpha carbon, one carbon away from the alkyne. And because this peak, this set B here is alpha to that, it should be somewhere between 2 to 3, which is good. Right, any questions on that? Okay. Now let's go over the next one, this one right here. So where do you guys expect these hydrogens to land on the HNMR when we have hydrogens directly on the alkene? Wait, you could use this chart here to figure that out. Right. Where would you expect these hydrogens here to be on the HNMR? Yeah, it's going to be between 4 to 6, right? The alkene hydrogens are going to be between 4 to 6. So let's see which one of these options here has a peak between 4 to 6. Okay, okay, not A, not B, not C. The only option is D. So based on that, I will automatically say that this is D. Do you guys want to analyze this molecule more to see why it makes sense? Let's do it for extra practice. Right. So this is gonna be A. This is gonna be D. But let me just analyze it for you guys so it makes more sense for future practice. Right. No, wait, no, not that one. D. Right here. Okay. Let's do the same thing. Let's draw out all of the invisible hydrogens and label them. Let's say A, B, C, and D. Right. There's 4 different unique peaks. Now, 4 to 6 is going to be the alkene hydrogens. So this is either going to be C or D, right? To figure it out, look at the integration here. This integration shows 1, which is going to be C, right? Because there's only 1 C hydrogen. This is going to be D because there are 2 D hydrogens, right? Now, the number of neighbors for this is going to be a little bit tricky to count because of something called complex splitting, which you'll know more in 118B, right? But given where these peaks are located at, 4 to 6, and the integration, we could say that this is C and this is D, right? We don't have to worry about this splitting pattern yet, right? Now, we could say that this is going to be B and this is going to be A, right? And notice where peak B is located at. Peak B is alpha to this alkene, right? Which means that peak B has to be at the alpha region between 2 to 3, which checks out, right? And now let's make sure that it has the right number of neighbors. We said earlier that it has 4 neighbors because it has 5, 1, 2, 3, 4, 5 subpeaks. So let's make sure that checks out. Right, let's start with this hydrogen here. 1, 2, 3. That's 1 neighbor. 2, 3, 4 neighbors. These are its 4 neighbors here. Right. So that checks out. Now for A, it will have 2 neighbors because it has 3 subpeaks. 1, 2, 3. So starting at either one of them, doesn't matter which one. If you go 1, 2, 3, these are its 2 neighbors here. Its 2 neighbors are those B hydrogens. Right? So that's how you analyze that. Right. Okay. So let's move on to the next one. Okay, so this OH right here, there should be a broad peak around 0 to 0.5 to 4, but there he said like if you're going to give no signal, so we'll just go with what he says. But where should, let's say, this hydrogen be located at? If it is direct, if it's attached to a carbon that's attached to an electronegative atom, right? Let's use the same graph here. Where would that peak be located at?
Is it between 3 to 4 if it's an electronegative atom?
Yeah, it's between 3 to 4. If it's an electronegative atom, right, which could be oxygen, nitrogen, fluorine, or bromine, right? So this we expect to be between 3 to 4. Let's see which one of these graphs here has I think between 3 to 4. 3 to 4. Not A, so get rid of that. B has something there, so keep that. C has something between 3 to 4, so keep that. D has nothing between 3 to 4, so get rid of that. Process of elimination for multiple choice. Right. So now let's look at B and C more clearly. Right. Let's see. Let's go back to this problem here. how many neighbors would this hydrogen have? Let me draw out the invisible hydrogens for you guys so it's easier to see. And another thing about the number of neighbors is that it has to be attached to a carbon. If a hydrogen is attached to a non-carbon atom like oxygen or nitrogen, that would not count as a neighbor, right? So how many neighbors would this hydrogen have right here? Neighbors. Right, so to calculate the number of neighbors, let's do that trick where we start at this hydrogen atom, right? And we go 3 bonds away. If it lands on a hydrogen, it counts as a neighbor. So 1, 2, 3. That's a hydrogen. That's a neighbor. 1, 2, 3. That's another neighbor, another hydrogen. 1, 2, 3. Another neighbor. 1, 2, 3. Another neighbor. 1, 2, 3. Another neighbor. Right. So that's 1, 2, 3, 4, 5 neighbors. If you go here 3, this lands on a carbon. Right. That carbon is not hydrogen, so that would not count as a neighbor. If you try to say that these are the neighbors here, these are too far away. That's 4 away. 4 away. Right. To be counted as a neighbor. Right. If you try going down, like let's say 1, 2, and then the third bond will land on a hydrogen. This hydrogen here does not count as a neighbor because it is on a non-carbon atom. It's attached to a non-carbon atom. It's bonded to a non-carbon atom. Bonded to a non-carbon atom. Heteroatom. Right. So if it has 5 neighbors, 1, 2, 3, 4, 5, how many subpeaks would you expect for that hydrogen to have in the HNMR? If are they counted as separate H's, even like if it's like C2 or C3? Yeah, they will be. That's actually a really good question because when you figure out the integration of peaks, right? Then no, they'll be counted separately as well. I think you're thinking of how many unique peaks there will be in this overall structure, which the overall unique peaks would be 1, 2, 3, 4. And this should be 5, but according to Ling, that doesn't show up in the HNY. So in this case, for Ling's exams, this peak, this right here, will have 4 different unique peaks. Where even though there are 3 hydrogens on that carbon right there, that counts as 1 unique peak, and that counts as 1 unique peak because they share the same chemical environment, right? But we're not figuring out the number of unique peaks here. We're trying to figure out the number of neighbors that this specific hydrogen has, which we have to count all the individual hydrogens 3 away, right? Even though there's 2 here, those will be considered separate neighbors, different neighbors. Right. Right. How do you know which hydrogen we start on? Is it a single atom that's attached to a carbon? So you could start on any hydrogen here. We could even start with this hydrogen here, which is part of this set, right? So you can start with this set here. And then if we do that, we go 1, 2, 3, 1, 2, 3. That will show that this set of hydrogens will have 2 neighbors, right? It just depends on what peak or what set of hydrogens you want to figure out how many neighbors it has, right? In this case, I asked you guys how many neighbors would this hydrogen have right here, which is why I started at this hydrogen. If I asked you guys how many neighbors do these hydrogens have, like this set of hydrogens have, then you would start with either one of these hydrogens here to calculate the number of neighbors. Right. So we see that this peak right here has 5 neighbors. 1, 2, 3, 4, 5. Count them as separate, even though they're on the same carbon. If there's 5 neighbors, what would the multiplicity be? How many subpeaks would you expect for this peak to have on the HNMR? How many subpeaks?
6.
Yeah, six subpeaks because of the n plus 1 rule. So now let's go back to the option choices. let's see which one, B or C, has 6 subpeaks. It looks like this one. 1, 2, 3, 4, 5, 6. 6 subpeaks representing 5 neighbors, right? Because neighbors, where is it? Where's that equation? Oh, right here. Neighbors would be equal to the number of subpeaks we have minus 1. 6 minus 1, 5 neighbors. So the answer for this would be B. Wait, this one here is a triplet. So that would have 2 neighbors, but we don't have 2 neighbors. We have 5 neighbors. So the answer for this would be B. Right. B, there should be like some kind of broad peak here as well, but yeah, it's okay. So did you choose that H because it's closest in proximity to the electronegative atom, and therefore the 6 peaks would be between 2 to 4? Because what if there was also 6 peaks at 2 or something? Oh, yeah, so that's a good question. I specifically chose the most interesting hydrogen, which is this hydrogen here. This is the most interesting hydrogen because it's going to be the most de-shielded hydrogen, the most like downfield hydrogen, where it's attached to the most electronegative atom, oxygen, here, right? Meaning that this hydrogen here is going to be on the most left side, which will be easy to identify compared to these boring carbon hydrogen bonds that are not bonded to an electronegative atom, right? That was the first thing I did to figure out the differences between those graphs, right? And because I know that this hydrogen here attached to a carbon attached to an electronegative atom is between 3 to 4, that's what I looked for, right? Like, given this graph right here, this hydrogen right here should be somewhere between this region, 3 to 4, right? But then when I saw the answer choices, B and C has something between 3 to 4, right? Where the difference between this, one of them is the number of subpeaks. 1, 2, 3, 4, 5, 6 subpeaks versus 1, 2, 3 subpeaks. So that's one difference you could go for, which is like the harder one. I just realized that there is an easier way to tell the difference between B and C, and that is integration, right? That's probably the easier way, because if you go back to this problem here, there's only one of those hydrogens in this set, in this peak, right? There's like only one of those hydrogens. There's no 2 hydrogens because that would make the oxide row. And because there's only one of those hydrogens that is unique to itself, then the integration should be 1, which is option B, right? Not 2. So yeah, that's probably a faster way. But this is still good to analyze for future NMR problems. Yeah. Because the most de-shielded, it will become the most left on the graph. Yeah, most de-shielded means it will be the most left side of the graph. This is the de-shielded region. Like the more left the peak is, the more de-shielded it is, and more to the right side is the shielded region. And there's no set region where it's shielded or de-shielded. These are relative terms, right? This peak here is more de-shielded than these peaks here, right? Or you could say this peak right here is more de-shielded than these 2 peaks, right? But this peak here is more shielded than this peak here. So it's relative. It's relative depending on what you're comparing it to. This is the most de-shielded peak because it's the peak that is to the most left side compared to all the other peaks in this graph, HNMR spectrum. Yeah. Okay, so that was the HNMR. Does he tell you to draw like the structure given an HNMR graph, or does he just tell you to match the things? Oh, he does. Okay. Yeah, so this recording will be posted as soon as I get the Zoom recording of it. I'll post it to the Discord first so you guys can review it earlier, but then it will be uploaded to YouTube with the timestamps sometime later. I'm not sure yet, but I'll post it to the Discord as soon as I can. Yeah. Draw a molecule given IR and NMR, or do we get partial points for fragments? ADO. Yeah. Okay, yeah, this is example on problem on page 5. And after that, I want to go over stereochemistry because one person requested that. Let me see if that person's there. Oh yeah, okay. Yeah. So yeah, I'll go over stereochemistry after this problem. Right. Okay. Question 5, problem 5. What? Oh, right here. Okay. Okay. Before going over that problem, let me give you the general guidelines to solve this type of problem here. Right. The first thing I do is I always calculate degrees of unsaturation, which is equal to 2 times C, 2C plus 2 minus H minus X plus N all over 2. Right. X is going to represent halogens like chlorine, bromine, iodine, fluorine. N is going to represent nitrogens. C is carbons. Right. That's the first thing I do. And DOU is basically going to tell you if you have unsaturation somewhere, like a double bond, a triple bond, or even a ring. It could be any kind of ring. It could be a 6-membered ring. It could be a 5-membered ring, 4-membered ring, 3-membered ring. Right. So how many DOUs would an alkene represent? Yeah. How many DOU would an alkene represent? How many DOU would an alkyne represent? And how many DOU would a ring represent? Could we also please go over synthesis, retrosynthesis, ABF? Yeah. So let's go over that after the stereochemistry part. Synthesis after stereochemistry. Yeah. Yep. Alkene would represent 1 DOU. Alkyne, 2, right? And then any kind of ring, 6-membered, 5-membered ring, 4-membered ring. So you're thinking about a special kind of ring, right? I'll go over that special kind of ring after this, but a ring will represent one DOU, any kind of ring, right? So you're thinking of benzene. Whenever you have a benzene here, we see that that benzene ring has 1 ring and 3 double bonds. 1 plus 3 equals 4. So this benzene, we have a DOU of 4. So whenever you calculate DOU, and it's at least 4, you most likely have this structure somewhere in your molecule, benzene. Right. So that's the first thing I do. The second thing I do is look at the IR for the functional groups, right? Not the specific things, but the functional group, which is that graph that I showed you guys earlier here, using that graph, right? Number 3, I would do is look for the HNMR specific fragments using a lot of different tools that they have, which is integration, how many hydrogens are in each unique peak, multiplicity or coupling, or the n+1 row, which will show you the number of neighbors that a peak has, right? And how de-shielded a peak is, de-shielding and shielding effects. Right. And that's using this graph right here that I gave you guys earlier, right here. Right. Okay, and after that, we
Oh my god.
connect the puzzle pieces together, right? Because this right here will give you like the fragments, right? The pieces to the puzzle. connect the fragments and pray that you get the correct specific structure. Right? There's a lot of trial and error in this step, right? Because there's a high chance that you won't get it right the first time. And then when you go back to verify the multiplicity, the number of neighbors, integration, you see that something doesn't match up. So that's when you have to try again until everything matches up to get the correct structure, right? But for these types of problems here, you get majority of the points by calculating DOU, the functional groups on the IR, like carbonyl, aldehyde, and the fragments from the HNMR, right? The hardest part is this like part right here, connecting all the fragments together to a specific molecule. Like that's very, very specific, right? And then after that, you gotta verify if you have the right structure. With the DOU, the IR functional groups, the HNMR information, the chemical formula. That's the first thing that I use to verify, right? Because this chemical formula will tell you how many carbons you have left, how many oxygens you have left, how many hydrogens you have left. Like that's the first thing I do, and everything else I do afterwards. DOU, IR, functional groups, HNMR information, chemical formula, and yeah, that's it. So these are the 5 steps that I do when I attempt on predicting the structure from IR and HNMR. Right. An alkane is going to be single bonds between carbons. Right, so that's an alkane right there. Right, you can also see it in this form. Like all of these are alkanes. Alkenes are double bonds. So that's an alkene. That's an alkene. Alkynes are triple bonds. They sound very similar, but they're different because of the bond order they have. Alkane has a bond order of 1, single bonds. Alkene will have a bond order of 2, double bonds. Alkyne will have a bond order of 3, triple bond. Oh, what is alkane? DOU is what I meant. DOU 0. Yeah. Alkane DOU would be 0. Like any alkane here with no double bond, no triple bond, no ring, right? No cycloalkane, then the DOU would be 0, right? Because this is saturated. There's no unsaturation. There's no double bond. There's no ring. Right? But a cycloalkane, like these here, cycloalkanes, they have a DOU of 1. Cycloalkane. Yeah. Okay. Now let's move on to this problem here. So I'll show you guys my thought process on this problem. I haven't looked at the key yet, so I don't know what the structure looks like. And if something doesn't make sense, let me know in the chat or the voice on the Zoom, and then I'll explain it from there, right? But for now, I'm just gonna say what I think about this problem. Alkyne is 2. Alkyne would be 2, right? Even though there's a triple bond, it will represent 2 DOU, 2 degrees of saturation. Alkene is 1 DOU. Even though there's 2 double bonds, there's 1 DOU. And alkane, right, is going to be 0 DOU. 1 bond, but 0 degrees of saturation. Unless it's a cycloalkane ring. Would a C double bonded to anything other than a C, like an O, count as a DOU 1 or DOU 2? Yeah. Right, so that's a good question, because if we have a carbonyl, like let's say this right here, carbon double bond oxygen, that would count as a DOU of 1, still a double bond. Doesn't matter if it's between carbons and carbons or carbons and oxygens. That's still a DOU of 1. DOU can be equal to pi bonds. Yeah, that's a good way to think about it. Alkene here, there's 1 pi bond, 1 DOU. Alkyne, there's 2 pi bonds, 2 DOU. Except cycloalkanes. Cycloalkanes have 0 pi bonds, but they still have a DOU of 1. Okay, let's go move on to the problem and then stereochemistry. So first thing I do, calculate DOU. 2 times 4 plus 2 minus 8. There's 0 halogens. There's 0 nitrogens. All over 2. Right? So that's 8 plus 2, that's 10. 10 minus 8, that's 2. That's going to give us 1 degree of unsaturation. So we either have a double bond or some kind of ring in the structure. Right? And because I know we have 1 DOU, I'm going to jump straight into the HNMR. Whoa, right here, right? And I see the 4 to 6 ppm range is the alkene range, right? With the hydrogen, like that. Let me show you guys that on here, which is, where is it? Right here. Oh, this part here, right? 4 to 6 is the alkene range. So I'm leaning towards that this 1 DOU here is most likely coming from an alkene rather than a cycloalkane. But we'll see, Okay. IR spectrum, HNMR spectrum provided below. Possible structure for the molecule. Give fragments with partial credits, yep. If your molecule is completely correct, you get full credit without providing any fragments of DOU, right? I wouldn't spend more than 10 to 15 minutes on this NMR problem, right? I would get the DOU partial fragments to get most of the credit. And then at the end, if you could get the full credit, that's just a bonus point, right? But I would like get the synthesis problems correct, the reactions correct, the nomenclature correct, the multiple choice ranking problems correct, drawing problems correct, right? And then the NMR, the correct structure, that's a little bit of the points, minor points. Right. For this problem here, it's much easier to get the DOU, much easier to get the fragments. So focus on where you get the most points at, and if you have time at the end of the exam, then that's when you go back to get to attempt to get the full structure. Right. So degrees of saturation is 1. Okay. Now let's look at the IR. That's the next thing I do. Look at the IR. Ignore this region. That's the fingerprint region. This is going to be around 1700. So that's the carbonyl. So, okay. Wait, 16, 17, 18, 19, 2000, 16, 17, carbonyl. But I said earlier we had an alkene, right? We can't have an alkene and a carbonyl at the same time because that would be 2 DOU, which does not match up with our 1 DOU here. So let's see, is it a carbonyl or is it an alkene? We'll see. But it's either one of these though. Okay, now 3000, that's the regular sp3 carbon hydrogen peak. Okay, so that's IR. Let's look at HNMR. 2 oxygens. Okay. So the more practice you do, the more patterns you recognize, and the more functional groups you can predict what's on there, right? Because I see 2 oxygens here, I'm gonna predict that this makes an ester. This molecule is an ester, which is something like this. The carbonyl next to some kind of OR group, right? I'm not too sure yet, but I'm leaning towards this molecule here. If it's not that, then it's going to be a carbonyl and some kind of ether, right? OR. But we'll see what it is. Like, there's a lot of guessing here. There's a lot of trial and error. Let's see. Ooh. This is high. Okay, so this HNMR freak right here, right? What functional group do you guys notice about that right there? Let's say it's around 9 to 10. Yeah, 9 to 10. Right, let's go back to that graph that I showed you guys. What functional group do you guys notice between 9 to 10? aldehyde, right? So that piece of information right there eliminates this option, ester, right? So we most likely have an aldehyde based on this peak right here. And these squiggly lines here are just showing that it's a fragment. Like, I don't know what's attached to her yet. Right. Okay. So since this is not an alkene peak right here, let's say that this peak right here is just showing around the 4 ppm range, which we said earlier. Right. So ignore the 4 to 6 alkene range. This peak right here is not like high enough for that. Right. The 4 to ppm range is going to be the D-shielded range, which is going to be a carbon, like something like this. Right. What X could be oxygen, fluorine, chlorine, or bromine. But in the chemical formula, we only have oxygen here. Right. So to draw this fragment out, look at the integration. There's 2 hydrogens. So let's draw those 2 hydrogens out. That's the integration, the 2 hydrogens here. Right. I'm going to put an oxygen atom right there. Wait, let me make this more clear. Oxygen, boom. There we go. Okay. So this oxygen here is making this peak of 2 hydrogens D-shielded, which is why it's around the 4 ppm range. Right? We see that it has 3 subpeaks, 1, 2, 3, which means that it will have 2 neighbors. 3 minus 1, 2 neighbors. So I'm going to draw its 2 neighbors out like this. Right? So its 2 neighbors are going to be right here. Would the peak near 3000 be aldehyde? 2700, right? Because if we have an aldehyde peak on the HNMR, on the IR, there should be a sharp peak at around 2700, right, from the IR graph here. Yeah. At 3000, there should be a sharp peak to the right of the 3000. Yeah. Okay. So its 2 neighbors are going to be these 2 hydrogens right here, which I'm going to say is these 2 hydrogens here, right? Is that peak right there. And we see that it is not as D-shielded because it's far away from that oxygen, right? We see that those 2 hydrogens will have 1, 2, 3, 4, 5, 6 subpeaks, which means that it will have 5 neighbors, right? We already see 2 of its neighbors, which are these 2 neighbors right here. So that means that we have a terminal methyl group here, or not methyl group, but terminal CH3 here. Right. To show its 5 neighbors are 1, 2, 3, 4, 5 for these 2 hydrogens here, representing this peak here. Right. Now let's make sure that these 3 hydrogens here are actually these 3 hydrogens right here. It has 1, 2, 3 subpeaks, which means that it will have 2 neighbors, which checks out because these 3 hydrogens here will have 2 neighbors, which are these 2 hydrogens right there. Right. So this is one end of the chain that I think is going to be in the molecule. Right. Let's see how many carbons we used up already. We used up 1, 2, 3 carbons. And this is the 4th carbon here with the aldehyde. So I'm just going to connect the pieces together like that. And say that my overall structure is going to look like this. 1, 2, 3. H. Wait. Hold on. I got to make sure everything else makes sense though. How many hydrogens do we have? We have, wait, sense. 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So that counts. That checks out. 4 carbons. 1, 2, 3, 4. That's good. 2 oxygens. That's good. 1 DOU. That's good. The carbon of 1 oxygen. We have the aldehyde hydrogen here, represented by this peak in the HNMR. two hydrogens right here that are next to this electronegative atom, d-shielded, is this two hydrogens right here with two neighbors. These two neighbors in between with five neighbors are going to be that peak. And then three hydrogens here with two neighbors is going to represent that peak right there. But this looks very weird though, because I've never seen, this looks very off. Yes, I've never seen an aldehyde and an ester together like that. Right, which is why I crossed out this ester option at the earlier because I don't usually see an aldehyde and an ester combined like this. Wait, let me check the key. Wait, but this is what I would put on the exam. Let's see. Where is it? Oh yeah, okay. So yeah, this is the structure, but it's very weird. Yeah. Did that thought process make sense? On how I predicted this molecule given the IR to tell what kind of functional groups we have, which we saw was this C110 and 2700 aldehyde peak, and then HNMR to figure out like the fragments, the puzzle, the pieces of the puzzle, and then I throughout the process I counted how many carbons we used up. I saw that we only have a limit of 4 carbons, so from this peak right here, I saw that we already used up 1, 2, 3, 3 carbons, which leaves us with one more carbon, which comes from this carbon on the other fragment I already used up. Right, so I just try to connect those two pieces together to get this full structure here. And then throughout that process, like I used the HMR neighbors integration to figure out the components of this piece right here. Right, the most like distinguishing feature about this is these two hydrogens right here that are very d-shielded, because those two hydrogens right there are next to that electronegative atom, which is going to be between 3 to 4 here, right? The most d-shielded ones. So the d-shielded peaks right here is going to tell you the most clear sign of what the molecule will look like, right? Automatically, when I saw a peak here between 9 to 10, I automatically knew this was an aldehyde hydrogen, right? Which is this right here. And then from this right here, around the 4 range is the electronegative range, right? Where it's next to an electronegative atom. And our only electronegative atom in this example is oxygen. So I just put oxygen there. We don't have nitrogen. We don't have fluorine, bromine, iodine, any of that. So don't worry about that. Right. Once it gets more shielded, right, these are the more confusing ones to figure out, which are these ones here, because there's nothing interesting about it. There's no electronegative atom nearby. There's no functional group carbonyl. There's no alcohol. There's no carboxylic acid. Right. These are the boring ones where you have to actually figure out the number of neighbors and the integration to get the specific hyperspecific molecule here. Right. So first, like look for the most interesting ones, the functional groups and the most de-shielded regions, and then everything else will just build on each other. We could try another HNMR practice problems, or actually, yeah, let me move on to stereochemistry. Katya, are you still here? Okay. Yeah. So before we move on to that, any questions on this? HNMR IR stuff? Okay. Okay, now let's go over stereochemistry of rings and then move on to synthesis, retrosynthesis, synthetic analysis. Okay. Let's see. Let's start with this molecule here. How many chiral centers would this molecule have? Yeah, 2 chiral centers. 1, 2. Right. Is there a plane of symmetry in this molecule? Right, there is, which is going to be down that middle, because everything on this side is going to be the same thing as everything on that side. And based on that information, is this overall structure? Don't look at the specific carbons. Chiral or achiral? Achiral. Achiral. Right. Because of the plane of symmetry here. That plane of symmetry makes it achiral automatically. Right? For something to be chiral, that molecule has to have at least one chiral center and no plane of symmetry. Yeah, you got like 5 chiral centers, and then if there's a plane of symmetry, then that overall structure is automatically achiral. Right? And then chiral molecules will have optical activity. So you might see the question asked, which one of these molecules have optical activity? Whenever you see that, it's asking for which one of these molecules are chiral. Right? Achiral. Yeah, so achiral is going to be like, let's say, either no chiral centers at all, or they do have chiral centers, but with a plane of symmetry. Right? And then achiral things will have no optical activity. Right. So let's do some practice on this, and then move on to synthesis. Let me try to pull up the ones with rings. Where is it? Right here. This one. Nope, not that. This one. Oh, here you go. Okay. Curve flip. No. Hey, okay, let's do this one here. Okay, this is from one of my content review session notes when I did it winter airdrop. Yeah. Could you go over? Oh wait. Oh shoot. Oh yeah. Go over miso too. Yeah, we'll go over miso. What happens if one is wedge and the other is dash? Which is gonna be included in this practice problem, is chiral. Okay, no, Sean Mia got that question. Let's see now. Thing. When can it be a chiral but not a miso molecule? A chiral but not a miso molecule. Yeah, so I'll go over that too. Could you go over the chair in the practice find out for chirality? Okay, yeah, let's do that. Let's go over this first. Okay, let's label these parts A, B, C, D, E, F, G, H. Which one of these will have optical activity? Right, and then while you guys work on that, I'll answer the other questions. So a molecule to be achiral, but not a meso molecule would be if the molecule has no chiral center. No chiral centers at all, right? Because meso molecules will have chiral centers, most likely 2, with a plane of symmetry. That's the most important feature about mesomolecules, that plane of symmetry, right? Which makes it achiral, because mesomolecules are achiral, right? This is achiral. But to be achiral and not meso, not meso. Let's see. No plane of symmetry. No plane of symmetry. So an example of that would be something like this. Right. This structure here is achiral, but not meso. Achiral, but not meso. Because there are no chiral centers at all. Right. This is not a chiral center right here, because these two groups are the same. There are ethyl groups. This one on the right is not a chiral center because there are two methyl groups. Okay. Did you guys get an answer for this question? Let's see. Right. So the question is asking for the molecules that have optical activity. And we said earlier that the molecules that have optical activity are going to be chiral, right? And for something to be chiral, they have to have at least one chiral center, 1+ chiral centers, with no plane of symmetry, right? For it to be chiral and have optical activity. Right. Now, let's look at A. Is A chiral or achiral? Chiral, right? Because there are two chiral centers and no plane of symmetry. So let's circle that. What about B? Is B chiral or achiral? So this is a tricky one here, right? There are chiral centers, which are these chiral centers right here, right? But this is a sigma bond or a single bond that could do free rotation. If we rotate that single bond right there, the structure that we would get is going to be this, right? Keep everything on this left side the same. I'm rotating this side right here, right? So this side is the same. I'm going to swap this methyl group with that alcohol. So the methyl group is now going to go down and the alcohol is now going to go up. But when I do that swap, this dash gets converted to a wedge, right? When I rotate that. And then it's more clear to see with a model kit. But imagine this alcohol going away from you. If you rotate it up, it's going to go towards you now, right? And because of that, there is a plane of symmetry down here. Why is the first carbon on A chiral center if there are two CHs bonded to it? Oh, right. This first is a chiral center because there are 4 different groups attached to it. Right, let me draw out that hydrogen right there. And its 4 different groups are this isopropyl, this hydrogen, this methyl, and this whole thing right here with the bromine is considered one group attached to this one chiral center here on the left. Right, this CH is not the same as that CH. They're different because they're attached to different things. Right. Great. So this one right here would be considered achiral and meso, right? Meso because of that plane of symmetry down here. Right, and it also has two chiral centers. For something to be meso, they need to have at least two chiral centers, most likely two chiral centers, and plane of symmetry. Right, those are mesomolecules. Something that have two chiral centers and a plane of symmetry. This one right here is achiral, but not meso, right? Because there's no chiral centers at all, no chiral centers at all. How do you know when to rotate things around? So the big sign for that would be if you have two of the same groups and single bonds everywhere, right? So let's say we have something like get rid of that. This, right? A big sign would be if you have two chiral centers, one's a wedge, one's a dash, and you see no plane of symmetry, like as it's drawn, right? Then that's when you know when to rotate things. And you're going to rotate the bond between the two chiral centers, right? This is one chiral center, this is the other chiral center. The bond between the two chiral centers is the bond that's most likely going to be rotated to swap these two groups and get this rotated molecule here. When we swap that, the dash inverts to a wedge, and then the flat thing just goes down there, where the plane of symmetry is now here. Right. That's the time when you'll rotate things to figure out if this molecule is chiral or achiral, right? But now, if the problem, they can be tricky here. If the problem asks you like if this molecule here is chiral or achiral, and then you see both of these groups are wedges, they have the same stereochemistry, right? Some people, they will automatically say that this is achiral because they're so used to seeing that rotation thing, but there's no plane of symmetry here, right? If we rotate it to make it more clear to see like where the plane of symmetry might be at, this is what we would get here. The wedge stays on the top, stays stationary. But when we swap these two groups right here, that wedge gets inverted to a dash. And because that's a dash, there's no plane of symmetry anymore. That is no longer a plane of symmetry because this isopropyl group is facing up towards us. This isopropyl group on the other side is facing down away from us. No more plane of symmetry. So you have to be careful here, right? Be careful on how they give you the structure, which might be one of the other ones that I gave you guys here. Let's see. Yeah, it is. It is. Oops, but we'll go over that. You guys already know it, so that's good. That's good. Yeah. So let's look at C. Would C be considered having optical activity or not? Right. So this one is another tricky one. How many chiral sensors do we have in this molecule? And is that one you're saying this one right here in the middle? Zero, right? Because this group here is the exact same as this group right here. Zero chiral centers. Zero chiral centers, automatically achiral. No optical activity, right? Even though there are wedges and dashes, that's misleading. That does not mean that it is going to be a chiral center, right? This is not a chiral center because two ethyl groups, this is not a chiral center. Two ethyl groups, this is not a chiral center. Two weird looking things. So on rings, one wedge and one dash next to each other is generally chiral, but on straight chains, it's achiral because of rotation. Yeah, right. Right. Right, right. And that's this case right here, D, right? Because if you try doing that same technique that I showed you guys earlier, where you see one wedge, one dash with the same group, and you try to rotate it, you cannot do that because this isn't a ring. You can't rotate rings. You can't rotate double bonds. You can't rotate triple bonds. So it's stuck there. It's localized there. So if it's stuck there, there's no plane symmetry at all, making this achiral. Wait, wait. No plane symmetry, meaning that it is chiral, right? Because we do have chiral centers, right? No plane symmetry, chiral optical activity. Right. You can't rotate this. You can't rotate that bond because it's in a ring. But what about E? Is E considered having optical activity or no optical activity? How do you count the groups for chiral centers on rings? Yeah, so let's look at this chiral center right here. Right. Let's draw out the invisible hydrogen. This hydrogen here is a dash because the bromine is already a wedge. The wedge is taken. On the other chiral center, the hydrogen is a wedge because on that chiral center, the dash is taken by the bromine. Let's focus on this first chiral center here. Oh, that's another thing. This is tricky, right? Because one group would be the bromine, the other group would be the hydrogen, right? Now, look at the very first atom attached to that chiral center, which is this carbon, right? So let's compare this carbon and this carbon right here. Do you see a difference between those two carbons? Yeah, if there's a difference, right? Then that will be its own group and that will be its other group right there. The way I'm circling it here is like kind of weird, but you could circle it like that or like this, right? But then this ring here is just extra. Right? Does that make sense? Like they're considered different groups because they're attached to different things. Let me see if I have an example problem. Oh yeah, I do. Okay. So segueing off of that, yeah, focus more on the immediate bonds, right? Where you have to look at the very first atom first attached to the chiral center. If you see a difference, then they're automatically different groups. If you see no difference, then you move on to the next atom. If you see no difference, move on to the next atom, right? So segueing off of that, let's try G, right? And let's look at this chiral center. Wait, no, I can't say that. How many chiral centers are in the structure here? Right, are this ring here? Zero, right? Because if you look at this carbon here and see how many unique groups it has, this is one unique group, the isopropyl. This is another unique group, a hydrogen. If we look at the very first atom attached to that chiral center, they're the same thing, no difference. So move on to the next thing. Compare this one with this one, same thing. Move on to the next one. Right? They end on the same carbon, which makes this group the same as this group here. Two equal groups, they're not unique, not a chiral center. We can say the same for the other chiral center here. There is an alcohol, there is a hydrogen, and these two groups here, since there's a tie on the first carbon, look at the next one, tie on the next carbon, look at the next one, lands on the same thing, same thing. So these two groups here are also the same. So no chiral centers. Okay. And if there's no chiral centers, this is achiral, no optical activity. Right. So the rings here are very tricky, right? Because of like the plane of symmetry. Oh wait, that's another way to say it's achiral, right? There's a plane of symmetry going down here. There's no chiral center, and there's also a plane of symmetry here. we can't say this is meso though, because these two groups here on the oh no, yeah, this is not meso at all, right? Because for it to be meso, there needs to be chiral centers. There's no chiral center, so we can't say this is meso. But there is a plane of symmetry and 0 chiral center, so that's like double achiral. This is very achiral, very very much so. Right. Okay. Now let's try E. Does E have optical activity or no? No, right? Because there is a plane of symmetry here. Are there chiral centers? And if so, how many? Two chiral centers, right? One here and one here. And if we have two chiral centers and a plane of symmetry, it's achiral. But what kind of achiral is it? What kind of yeah, meso, achiral and meso. Nice. Okay, how about F? Does F have optical activity? Wait, for Ling, did you guys learn about ether reactions or did you guys just end at alcohol reactions? So then I know what to put for the synthesis funds for you guys for this last part of the review session. Like ether reactions with strong acid. Oh, you guys learned ether reactions. Okay. Okay. Williamson ether synthesis. Yeah. And also epoxides, right? Epoxides with acidic and basic conditions. And if it's acidic, it attacks the more subside of the epoxide. If it's basic conditions, it attacks the less subside. Does that sound familiar? I'm not sure. If you guys went over that or not. Chiral, because they're both dashes. Yeah, chiral because they're both dashes and there's no plane of symmetry. But you can't say that's a plane of symmetry because they're not the same. That's good. That was the tricky one. Some people would have said this was a achiral because they tried rotating that bond, which if you did rotate that bond, this is what you would get. Like that stays the same. This dash gets inverted to a wedge, right? Now there's no plane of symmetry there. But if you look at this example, one is wedge, one is dash. When you rotate it, both are wedges. Or if you rotate the other way, both are dashes. Nice. So be careful of the differences between those. Right. And because this is chiral and has optical activity, right? We are going to circle this as the answer, one of the answers. Yep. Okay. Now let's look at this last one here. Is this last one chiral or achiral? Does it have optical activity or does it not have optical activity? Yeah. This here has two chiral centers. One is here. The other one is here. Right. This is a chiral center because it has a bromine, hydrogen, ethyl, and this weird structure here. Right. This is a chiral center because it has a hydrogen, a bromine, a ethyl, and this weird big bulky group there, right, on that chiral center. 4 different unique groups, 2 chiral centers. Yeah, it does rotate, and we do have one wedge, one dash. But what do you notice about these two groups right here? So let's say we did rotate it. Right, we get that. This wedge stays as a wedge. Keep that stationary. This dash gets inverted to a wedge. But like, what do you notice about these here? Is there a plane of symmetry from here? Like, is this considered a plane of symmetry here? They're different, right? Different groups. So that's another to look out for. This, even though like it can rotate and have the same stereochemistry like this, they are achiral. Oh wait, this is chiral because there's no plane symmetry. This is different than that, so that's not plane symmetry. They're different. Yeah. So be careful of that. That was a sneaky one. Right. And we also said this was chiral as well because you cannot rotate that bond. No plane of symmetry. And 2 chiral centers, right? there's two chiral centers, one here and one here. But for something to be chiral, it only needs one chiral center, right? At least one. This one has two chiral centers though. F is chiral. Yep, F is chiral. It has optical activity. So the ones I circled in red are chiral and has optical activity. These ones here have no optical activity, either because they have a planar symmetry or because they have no chiral centers, right? This one here, C, has no chiral centers. And it also has a planar symmetry here. And this one here, it does have two chiral centers, but because there's a planar symmetry there, it automatically makes it achiral because of that planar symmetry, even though there are chiral centers. Yeah. Okay. Any other questions on the chirality stereochemistry stuff before I move on to synthesis, retrosynthesis, alcohol, ether, oxidation, reduction, SN2, SN1, E1, E2? Do wedges and dashes matter for chirality when they are not next to each other? Yeah, so they don't have to be next to each other. It's just easy to see in that case. I'll give you one where they're not next to each other. Right. Now let's do a exercise here. Let's say this is A, B, C, D, E, F. Between what atoms, like, do you want to rotate? What bond do you want to rotate between what atoms to draw the structure that is clear to see the planar symmetry at? Between bonds A and B, I mean atoms A and B, B and C, C and D, D and E, or E and F. Like, what bond do you want to rotate to show this planar symmetry more clearly? C and D, right? So they don't have to be near each other. They can be far away from each other, right? And then when we do that, keep everything on the left side the same, stationary. C and D, this is the bond here that's rotating, and if that's rotating, I'm gonna rotate this, go down, boom, 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 boom. Oh, it's missing something. Boom, 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 boom. Right. This is A, B, C, D, the bond we rotated between C and D. E and F. F had this dash alcohol, but that dash alcohol is gonna invert into a wedge alcohol because we're rotating it, swapping it. Right, where we see the planar symmetry between C and D, like that. Could you do some quick review on R and S? Yeah, so, okay, this next 5 minutes is gonna be, or 3 to 5 minutes is gonna be a quick review on R and S, because I want to move on to the synthesis and retrosynthesis stuff, because that's a big part of the final. There's 3 scenarios to do that, right? But the first thing you do for R and S, look for the lowest priority group, which is the one with the lowest atomic number. And there are 3 scenarios. The first scenario is going to be the easiest. Second scenario is intermediate. Third scenario is the hardest, right? So let's look at this one here. So there is a chiral center here. First thing, look at the lowest priority group, which is this hydrogen right here, right? We want that lowest priority group to be on the back side to assign RNS, right? This is the easiest case, easiest example, because the lowest priority group is already on the backside, the dash. So we don't have to do anything. We don't have to flip anything. We don't have to rotate anything. Then we can do everything normally. Assign priority based on atomic number. Oxygen has the highest atomic number, so that's 1. There's a tie between this carbon and this carbon. So if there's a tie, look at what's directly attached to it, right? So let's look at this carbon right here. Ignore the bond to the chiral center. That carbon is attached to 3 hydrogens. 1, 2, 3. Now let's look at the other carbon. This carbon, ignore the bond to the carbon center. It's attached to one carbon and two hydrogens. One carbon, two hydrogens, right? And the way I list this is that I list the highest atomic number at the top. Carbon beats hydrogen. So this is going to be number 2. This is going to be number 3, right? Rotating this way is counterclockwise, so that's S. We don't have to rotate anything. We don't have to flip anything because the lowest particle group is already on the backside. That's the easiest example. For number 2, let's say the lowest particle group is on a wedge this time. Right. Okay. Oh wait, no, that's not that kind of sensor. Let me do, boom. Okay. Okay. So lowest particle group is on a wedge. If the lowest particle group is on a wedge, to save time, do everything normally, then flip it at the end. Right, so that's gonna be 4. There's a tie between this carbon, and this carbon. This one carbon here, ignore the bond to the carbon center, is bonded to one carbon, two hydrogens. This one carbon here is also bonded to one carbon, two hydrogens. But this one carbon right here is bonded to carbon 2 times and 1 hydrogen, right? Because of the double bond here. This double bond will count as 2 bonds to that one carbon, which is that 1, 2 right there, right? So that will show that that's number 2. Now let's look at this here. Let's move on to the next atom. This carbon to the right is bonded to 3 hydrogens. This carbon bonded to at the left is bonded to 2 carbons and 1 hydrogen, right? Carbon beats hydrogen, so that's number. This is supposed to be number 1. This is supposed to be number 2. This is number 3. Okay. Going this way, it will look R. It looks R, right? But it's not actually R because our lowest particle group is on the front side. We don't want that. We want it to be on the back side. So we flip it to S. It looks R, but is actually S, right? So this is S right here. And you can only do this trick to flip it only if the lowest particle group is on a wedge. That's the only time you can do that, right? If there are an odd number of carbons away, would it be chiral if there's one wedge and one dash? This one is even, so it would make it chiral. Yeah, right. If the distance is like asymmetrical, then it would be chiral. Because if it's asymmetrical, if you try to rotate it, there's no plane symmetry that's gonna happen. Right? Like let's say this alcohol here is like 1 away. And an extra carbon right there. If you rotate it, no symmetry, no more plane symmetry. Or even if you added extra carbon here, no more plane symmetry. They're going to be different groups, right? Okay. Now the hardest example is when the lowest particle group is on a flat bond, not a wedge, not a dash. Right. So this is our chiral center right here. Our lowest particle group is on the flat bond. This is number 1. This is number 2. This is number 3. Right. Now to assign R and S, you cannot do it right away. Like if you say 1, 2, 3, that's S. That could be right, but that's not the right way to do it. What we want to do is rotate these groups right here. So anchor the other flat bond down. Keep this group stationary, right? Keep it still. Hold it still. The groups that you're going to rotate are this hydrogen, this alcohol, and this methyl group right here, right? Because we want the lowest particle group to be on the backside, I'm going to rotate this, what is that? Counterclockwise? Yeah. Rotate the hydrogen on the dash, the methyl to be on the wedge, the alcohol to be on the flat bond, right? Now, after the rotation, we get this. So this group right here will stay the same. It will stay still. The dash bond will stay still. The wedge bond will stay still. And the flat bond will stay still, right? The things that are rotating are the groups on those bonds. The dash is now the hydrogen. The wedge is now the methyl. And then the flat bond is now the alcohol, right? Now we can do everything normally. This is now back at scenario number 1, where the lowest particle group is on the backside. So 1, 2, 3, 4. Going this way is S. So it turns out, like in this specific example, that if you do it normally, then you get lucky, you get the right answer anyway. Okay, so that's the hardest example. But there are some examples where if you do it like this without doing any rotation, you get the wrong answer, right? Because we want the lowest particle group to be on the on the backside. Okay, ready for synthesis, retrosynthesis, retrosynthetic analysis stuff? Okay, let's do it. Do you guys like, how do you guys want to do this? Like, have me walk through the synthesis on the final and then go from there, like teach you the like what to look out for. Okay, what column is it on the final? Let's see. Mm, no, no, this one here. Oh, this is mechanism, not synthesis. Uh, this is mechanism. Oh, synthesis. Okay. Oh, synthesis right here as well. Okay. Okay. Okay, so let's do some synthesis here. So the usual structure for this, like the question type synthesis, is they'll give you a reactant like that, and they'll draw a long arrow to the product that they want you to transform that reactant into. And there's going to be multiple reactions that would transform that reactant into this final product here, where the in-between stuff are the intermediates, right? And the stuff on the arrow are the reagents to carry out those reactions. It could be one reaction, it could be two reactions, three reactions, four reactions, five reactions, many reactions, right? So the first thing I'd look out for is the similarity between the reactant molecule and the final product, right? General tips onto, okay, yeah. So the similarity here is going to be this 3-carbon chain, 1, 2, 3, 1, 2, 3. Now the next thing I look out for is the differences. What are the differences? The differences are the groups on this 3-carbon chain. The reactant has a carbonyl, carbon double oxygen. The final molecule has a halogen, right? So that's the difference there, right? Now, for these synthesis problems, think of all the reactions you've learned as your tools in the toolbox that you're going to use for the synthesis problem, right? You have to really know your reactions here. But to help figure out what reactions you need, there's this thing called retrosynthetic analysis where you can go backwards, right? We see we have a halogen here that came from some kind of oxygen, right? Do you guys know a reaction that makes a halogen from some kind of alcohol? Oh shoot, some kind of oxygen functional group. So I already said it. Like let's say we go backwards here. Go backwards. Right? Do you guys know a reaction that can convert this alcohol into a halogen, like chlorine or bromine? Yeah, HCl is one. But in this case, there's no risk of carbocation rearrangement because once we protonate it, leaving group leaves, the carbocation is already at its most stable position, right? So no risk of protonation, hydride shift. There is a safer way though, because let's say your reactant was like this. If you use HCl, then your Cl would be shifted, right? SlCO2, which would not do any carbocation rearrangement, right? But HCl would work in this specific example because there's no risk of hydride shift. So if you use HCl in this example, it would work. But just be careful in other reactions, HCl would shift the carbocation to a more stable position, right? Now, do you guys know how we can convert a carbonyl into an alcohol? So this carbon here used to have 2 bonds to oxygens, but now it got rid of 1 bond to oxygen, it gained a bond to hydrogen. Is that oxidation or reduction? Right. How come when you added SlCO2 it becomes OH? Oh, wait. So I'm not going backwards here, right? I'm not doing this. I'm not reacting this functional group with SlCO2. I'm reacting this alcohol with SlCO2, which becomes this. Right? That's retrosynthetic analysis. I'm going backwards here. Right? Where this is the product that I'm saying the intermediate that made that product is this right here. Like what came before that is that right there. Does that make sense? Right. So when I add SOCO2, it would become Cl, because that's one of the alcohol reactions that you learned. Where, let me just do this here. OH, SOCO2, that would convert the alcohol into chlorine. PBr3, that would convert the alcohol into bromine. If you do PI5, that would convert the alcohol into iodine. I highly doubt you need to know the mechanism for this. It's just more of a recognizing the reagent and the reactant and what it does, right? If you see alcohol reacting with either one of these weird reagents here, that's going to convert the alcohol into a halogen depending on what the reagent is. SOCO2 would convert it to chlorine, PBr3 would convert it to a bromine, PI3 would convert the alcohol to an iodine, right? I don't think you need to know the mechanism for that unless you went over it, but I don't see it tested that much for 118A. Right. Okay. So now, to go from here to here, what is that transformation called? Did we oxidize it? Did we reduce it? Did we do an acid-base reaction? Did we do an SN2, SN1, E1, E2 reaction? Reduction, right? And what reducing agents do you know that can do that reaction? Right, it's one of those weird letters. Addition of H minus, right? Hydride ion. So you could either use Li, lithium aluminum hydride, or sodium borohydride. Second step, H plus. Right. Now, for these redox reactions, let me actually go over that with you guys because this will help you on the synthesis. And let's separate them into different alcohols. Let's say we have a primary alcohol, secondary alcohol, and a tertiary alcohol. A primary alcohol would be when we have an alcohol bonded to a carbon that's bonded to one other carbon. A secondary alcohol is when we have a carbon that's attached to the alcohol bonded to two other carbons, right? Two other carbons. A tertiary alcohol is going to be when we have a carbon that's attached to the alcohol bonded to three other carbons, right? Now, let's do oxidation. There are two oxidizing agents that you need to be familiar with in 118A, PCC and Jones. Right? PCC is a weaker oxidizing agent, which if you have a primary alcohol, that's going to transform the alcohol into an aldehyde. Jones is a stronger oxidizing agent, so that's going to fully oxidize the primary alcohol into a carboxylic acid, right? This is a stronger oxidizing agent because we see that this carbon here has more bonds to oxygen in the final product. This is a weaker oxidizing agent because we see that the final product here only has 2 bonds to oxygen and 1 bond to hydrogen, right? Now, this primary alcohol here is the hardest example that you need to worry about because once you move on to secondary alcohol, it does not matter if you use PCC or Jones, you get the same exact thing, which is a ketone, right? And then tertiary, PCC or Jones, no reaction, because for this reaction to occur, right, if something gets oxidized, something has to get reduced, right? And the meaning of oxidation is gaining a bond to an electronegative atom like oxygen right here, right? And the meaning of reduction is reducing the bond to electronegative atom or gaining a bond to hydrogen, right? We see that for this alcohol to get oxidized, it has to donate or lose hydrogens, right? In order for it to gain oxygen to conserve the octet rho oxygen bond. This carbon here has no hydrogens, right? So there's no hydrogens there to donate for something to get reduced, right? Even if you try to make a carbonyl on that carbon, that's not going to work, right? Because that breaks the octet rho. This carbon will have 5 bonds. So those are the oxidation reactions that you'll see. And Jones, you might see that in different forms like Na2CR2O7H2SO4 water, or you might even see CrO3H2SO4 water, or NaCrO7H2SO4 water. Like all these variants are variants of Jones. And the most important thing to look out for is the chromium and a lot of oxygens. Chromium and a lot of oxygens. Chromium and a lot of oxygens. If you see a lot of oxygens, strong oxidizing agent. Oxidizing agent, right? Okay, so that was oxidation. Now we could go backwards, which is reduction, which I'm gonna do in pink, right? Let me actually do this. This is oh my god. Let's see. Weak oxidizing agent, PCC. Strong oxidizing agent, Jones. And then the differences in what it does to the alcohols are going to be given in this chart here. Okay, now let's go over reduction. In 118A, a weak reducing agent would be sodium borohydride. Strong reducing agent would be lithium aluminum hydride. Right, so in 118A purposes, NaBH4 cannot reduce carboxylic acids. Right. Yeah. You'll learn more about these oxidizing and reducing agents more in 118B and C. But in 118A, NaBH4 cannot reduce carboxylic acids. It's not strong enough. LiAlH4 is strong enough to reduce everything though. Right. So if you try to go from an aldehyde to an alcohol, it doesn't matter. You could use NaBH4 or LiAlH4 as a reducing agent. Right. Now, to convert a carboxylic acid back into an alcohol, you cannot use NaBH4, right? NaBH4 will not do that. You would have to use LiAlH4, lithium aluminum hydride, right? If you tried using NaBH4 and acid workup, which could show up on the exam, put this as your answer, no reaction, right? That's a no reaction, right? Ketone, that's not carboxylic acid. It could be reduced by NaBH4 or LiAlH4. Plus, yeah, there's nothing to reduce there, so nothing to worry about there. Right, so carboxylic acid here, they require a strong reducing agent like lithium aluminum hydride to be oxidized back down. Right, and the reason why like this requires a stronger reducing agent is because this is more stable than the other things, right? Because of resonance. We could do resonance here. And resonance makes things more stable. And if things are more stable, they're less reactive. If it's less reactive, it requires a stronger thing to make it go through, which is lithium aluminum hydride, right? But yeah, just use this chart right here, which if you want to convert an aldehyde to a carboxylic acid, you can use Jones, right? Jones to convert an aldehyde to a carboxylic acid using Jones. So for 118A, these should be your oxidation and reduction reactions here. Okay. Yeah, so that's the synthesis problem for part A. Now let's do part B. Wait, I don't see. Why the step-by-step reactions? Oh, so for Ling's class, I think he wants you to do it like this. Right. But if you guys are taking leave-ins for 118B next quarter, the format you see synthesis problems is this. The reactant, long arrow to the product right there. And then draw the arrows, intermediate arrows that will transform this reactant into that product right there. Right. So let's do the same process. Okay, yeah, that's good. That's good that he showed you this right here. Right. Yeah, that's good. So the same process would be figure out the similarities. 1, 2, 3, 4. 1, 2, 3, 4. And then figure out the differences. The differences are like this is a single bond, this is a double bond. What reaction did you guys learn in 118A that makes double bonds, alkenes? Elimination, E2 reaction, right? And what is the reactant that is used for E2 reactions? Like SN2, SN1, E1, E2 reactions. What is the reactant? Like what's needed in that reactant? A good leaving group, right? So when we go backwards here, we can say that the good leaving group could be here or here, doesn't matter. Right? Now, what kind of strong base do we want to use to create this double bond right here? Right? We see that we made a more stable double bond rather than a less stable double bond. If we want a more stable double bond, would that be Zaitsev E2 or Hoffman E2? Right? Because this is the leaving group right here. This is the alpha carbon. This is the beta carbon. If we draw out the beta hydrogen, we see that we want to grab the more substituted one, which is going to be the Zaitsev E2, right? And to do Zaitsev E2, what kind of base, strong base, do we want to use? Unhindered strong base or hindered strong base? To get the unhindered one, right? So it could be any unhindered one. You could choose. It could be NaOH, water as a solvent, or NaOCH3 and methanol as a solvent, right? Okay. So now, how can you add a halogen to a regular alkane with nothing on it? This is one of the first reactions you learn in OChem. One of the very first reactions you learn. Yeah, bromination or halogenation. If I put bromine here, right, then you would do bromination or halogenation, Br2 and light. But if you put chlorine here, make sure that this is CO2, right? So it has to be consistent, right? But you could use bromination, which would put bromine there. Nice, nice. Two-step synthesis. Let's do this one. Oh, Grignard reagents. That's a very big important reaction for 118A. Okay, so first, let's figure out the similarities between these. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay, so for these kind of synthesis rounds here, when you see the carbon-carbon chain gets extended, it gets longer, then think of Grignard reactions, right? So the long extended chain is this extra thing right here, which extended the chain by 1, 2, 3 carbons. So we know somewhere in the reaction, we're gonna have this 1, 2, 3 Grignard reagent here, where this carbon attached to the Mg is the nucleophile, the partial negative thing. Yeah, this is the one with Grignard. Yeah, right. Right. So notice how I starred that electrophile, right? This is gonna be the dot electrophile that gets attached right here. Right. This is the nucleophile, I mean, the starred nucleophile and the dot electrophile right here. Right. And this is the new bond between them. Like this bond between the star and dot is gonna be the new bond that gets formed for the Grignard reaction. Now we see that there's an oxygen attached to that carbon 4 as well, right? Do you want to do a Grignard reaction right away? Like let's say we put a Grignard reaction right here right away, or do you want to convert this to something else first? Right? Because what would the product look like if we did this reaction right away? This is going to be the nucleophile. This is going to be the electrophile. The nucleophile would attack the electrophile, kick out the leaving group, right? So dot that, make a new bond between the star and dot, new bond between star and dot. The dot is attached to 2 other carbons, 1, 2. And that's a new bond between them, right? The star is the nucleophile, the partial negative charge. The dot is the electrophile, the partial positive charge. When this nucleophile attacks the electrophile, the star attacks the dot, we kick out the leaving group, and the MGBR dissolves away. Right? And this is what we get, right? But this is not what we want because we have a carbonyl right here, right? So the Grignard has to attack something else that would maintain that oxygen there, right? So besides attacking a halo alkane, what do you want to attack that with to maintain the oxygen atom? Grignards can be formed from haloalkanes, right? Because to form that Grignard right there, it could come from this haloalkane right here, where to form that, you just put magnesium in there, right? But Grignard here can react with a lot of things. It could react with a haloalkane, which is what I showed you guys here. It could react with a carbonyl, right? Or it could react with an epoxide. So 3 different electrophiles that this Grignard reaction can react with. There's more, but for 1,A, these are the 3 that this Grignard reaction can react with. Right. It doesn't want to attack an alcohol because, like, let's say we have this Grignard reagent here, RMGBr. This carbon attached to the Mg is the nucleophile, partial negative. Right. If we have some kind of alcohol there, there's no electrophile. There's no electrophile present in this molecule. No carbon to attack, no atom to attack. But we do want to form this alcohol here, going backwards. That's the previous step. So let's go backwards. Let's say that carbonyl came from an alcohol. What reaction did we just go over that would convert the secondary alcohol into a ketone? Yeah, no problem. PCC, right? Or Jones, because this is a secondary alcohol, it does not matter. If it was a primary alcohol, then it would matter what you use, PCC or Jones. Right. So to get this alcohol right here, let's say that alcohol is this dot carbon right here, which is that dot carbon on carbon 4. We want to make that carbon 4 electrophilic, right? We want it to be the partial positive charge somehow still. And when it gets attacked, it's still attached to an oxygen right there. To do that, we could say that this came from a carbonyl, a carbon double bond oxygen, right? So let's say this was the nucleophile star right here, the Grignard reagent portion, and this part right here was the electrophile portion. Right? And then let's make a cut between the star and dot carbon, right? Because you're gonna make a cut between the new bond that gets formed. And when we go backwards, we could say that alcohol came from this aldehyde right here, right? Now, to make an aldehyde, what can it come from? What kind of alcohol can it come from? Right? Like, what kind of alcohol did this aldehyde come from? Why is it a secondary alcohol and not primary? Yeah, so this is a secondary alcohol and not primary because the chain here is going to be extended where the alcohol is in the middle of that chain, in the internal side of the chain, where this carbon attached to the alcohol is bonded to 2 other carbons, 1, 2. And because it's attached to 2 other carbons, this is considered a secondary alcohol. Right, yeah, no problem. So what kind of alcohol do we want to form an aldehyde? We want a primary alcohol. And to create primary alcohol from this primary alkyl halide, we could use NaOH, right? And we got lucky here because this is a primary alkyl halide. If it was secondary, then you have to use like some acetate and then NaOH hydrolysis to go back. But that's a secondary alkane. This is going to just be SN2 reaction, where the OH minus is going to attack that electrophilic carbon, kick out the leaving group iodine to get to this OH here. And what kind of alcohol is this? Primary, secondary, or tertiary alcohol that we just formed from the SN2 reaction? Primary, right? Primary. And how can we convert a primary alcohol into an aldehyde? What reagent can we use? This is a primary alcohol because this carbon attached to the alcohol is bonded to 1 other carbon, primary alcohol. Right. And let's say that this is 1, 2, 3, 4. This is 1, 2, 3, 4. At carbon 4, we converted this primary alcohol into an aldehyde. PCC, right? We do not want to use Jones. If we use Jones, then we would get carboxylic acid, which is not what we want. Right. Now, this is where we do the Grignard reaction now. This carbon 4, which I'm dotting here, is the electrophile, the partial positive carbon. The reagent I'm going to bring in is this 3-carbon Grignard reagent, MGBr. with the acid workup step, where this carbon directly attached to the magnesium is partial negative charge. That's a nucleophile, right? I'm gonna show you guys the mechanism clearly down here to show you what's going on, right? From that step, that Grignard reagent, and then second step, acid workup. I'm gonna star the nucleophile, the partial negative portion. I'm gonna dot the electrophile, the partial positive portion. This nucleophile will attack that electrophile, but that's gonna break the octet rule for this carbon here, right? To conserve the octet rule, we're gonna pop this double bond onto that oxygen right there. Pop that double bond onto the oxygen right there to give that oxygen a pair of electrons, right? So after the result, we have this reaction. We have this dot carbon now attached to this star carbon, right? That's the new bond that was just formed from that reaction, that attack, new bond. Now, we're going to attach what is attached to the dot carbon, which is, it used to be attached to a double bond O, but now it is attached to a single bond O minus. It's an O minus now because it gained a pair of electrons from that bond right there. That bond represents 2 electrons, which got popped up onto that oxygen to give that oxygen a negative charge, right? Now, this star thing right here will be attached to 2 other carbons, 1, 2. Oh. 1, 2. The magnesium, just think of them as dissolving away in the mechanism, right? So that's the first step. Now the second step, acid workup. It could be H3O plus, it could be H2SO4, it could be HCl, any kind of acid is going to protonate this O minus. O minus will attack that H, that bond between H and O will kick out the water and give us, well, 1, 2, 3, 4. This reaction, this product here, this alcohol here, secondary alcohol, right? Which is this thing right here. And then we said earlier that that secondary alcohol made our final product using PCC. So the first reaction that we did was SN2 reaction. The second reaction we did was oxidation. The third reaction we did was Grignard reaction. The fourth reaction we did was oxidation again, right? So notice my general guidelines for these synthesis rounds here. Look for the similarities between the reactant and product, and then look at the differences between the reactant and product, and then go backwards. Retro synthesis, and then figure out what reactions are needed. And I don't always go retrosynthetically, like I don't always go backwards. I also sometimes go forward, right? Forward synthesis, right? And then I meet in the middle. Meet in the middle. So you could do both retrosynthetic analysis and forward synthesis, like going forward and going backwards, going forward, going backwards, one by one. And then the middle part would be more clear to you guys what is going on there. Williamson ether synthesis round, yeah. Let me go make a synthesis round for you guys. With Williamson ether synthesis, right? And then we'll end off there. So let's, before we go over that though, let me give you guys the reaction of Williamson. Are all of you guys taking 118B next summer session, or are you guys taking it in the winter of 2025? Williamson ether synthesis, or Wes? Next summer session, nice. So I did not do as well as I wanted to in the chiropractic like school midterms I had recently. So I decided to like only do office hours Monday, Tuesday, Wednesday, Thursday, 9 to 10 p.m. And not do like the review sessions for the midterms and finals anymore, because that's like taking like a lot of my time. But I will be consistent with the office hours Monday, Tuesday, Wednesday, Thursday though. 1 hour Monday to Thursday, right? So I'll still be here to help with the final or midterm, but it won't be like 2 hours. It will be like 1 hour Monday, Tuesday, Wednesday, Thursday. Right. Okay. So Williamson ether synthesis, the overall reaction is going to start from an alcohol, that's the reactant, and create an ether. The first reaction that happens is going to be an acid-base reaction. The second reaction that's going to happen is an SN2 reaction. This is the general reaction synthesis of Williamson ether synthesis. There's two, acid-base, second step SN2. Okay. Yeah, no problem. Okay. So an example for that would be something like this. Let's say we have this alcohol here, and you see two multi-step reactions. Let's say NaH and this alcohol halide here. Whenever you see NaH, or whenever you see Na in general, what charge does that associate with? What charge does Na associate with? Positive charge, right? Which means that whatever is attached to the positive charge is a negative charge. And this hydride ion here with the negative charge is extremely basic, very basic, strong base. That's a very strong base. That H minus is very unstable. Right? A negative charge on a very small atom, that's very unstable. If it's very unstable, it's very reactive, very basic. If it's a strong base, it's going to look for the most acidic hydrogen, which is going to be the hydrogen directly attached to the electronegative atom here, oxygen. Right? So the H minus is going to attack that H. I drew out that bond between O and H explicitly to draw this next arrow. That bond representing 2 electrons is going to pop onto that oxygen right there. Right? And then that's going to form this alkoxide ion with the O minus and H2 gas. But you don't have to put that in the product because that's not organic. That's not important. But H2 gas forms from this H attacking that H to become H2 gas. Deprotonating this alcohol into the alkoxide ion here, which, because this has a negative charge, that's a nucleophile. Now we're begin our second step, right? Which this is our electrophile. That's partially positive because it's attached to this electronegative atom. Nucleophile attack electrophile, kick out the leaving group. Right? So I'm going to star that oxygen to show that that's the nucleophile. Make a new bond between the star and dot, right? From the attack, that's the new bond that got formed. And then draw was attached to the dot, which is 1, 2 carbons, 1, 2, which formed an ether, alcohol to ether. Williamson ether synthesis. We synthesized an ether from an alcohol using 2 reactions, acid-base, deprotonate the alcohol into the alkoxide, and then SN2. Use that alkoxide nucleophile to attack the electrophile to form the ether reaction here. Right. Does that reaction make sense? If so, let's move on to one synthesis problem relating to this redox reaction, SN2E2, and one of the alcohol reactions. Okay, let's do that. I'll make one synthesis problem. So yes, it's gonna be like a little bit longer than what you see on the exam, but this is gonna be kind of comprehensive to what we did so far today in the session. Right. So let's do that here. Okay, let's see. Okay, so this won't have some of the reactions I wanted to go over, but this will have like a pretty good amount. Right. Let's see. Going over. Okay, so how do you guys feel about me going over the rest of the final after this problem? Like me just like walking through it, showing my thought process, and whatever doesn't make sense, you guys stop me by the chat or either the voice. Okay, I'll do that. Do that. Right. Okay, try this in this one. I'm gonna get water, and then I'll be back with the thought process. Okay, I'm back. Can someone tell me what they thought about this practice problem? You could either go forward or backwards here. You could go retrosynthetically, or you could go forward synthesis. And then yeah, it's okay if you guys get it wrong. That's how, like, other people might have the same mistakes, and we'll learn from those mistakes. Yeah, right. So to start off with this, we see that our reactant here has no functional groups, no ketone, no alcohol, no epoxide, no halogen, no good leaving group, nothing at all. Just regular old alkane, right? And this regular old alkane can only do one thing and one thing only, which is the very first reaction you guys learned, halogenation, which we could do bromination. Right? And why do I want to use bromination specifically? I want to use bromination specifically because bromine here is the most selective, which is going to select for the most substituted carbon, which is this carbon right here, the tertiary carbon. Right? Because at that tertiary carbon, there's a lot of things going on there. Like there's this new group here that we did not have before. Right? So yeah, we're going to start with halogenation to eventually get an ether. Okay, so one this carbon here is that star carbon right there. And this dot carbon is the new carbon that got attached. If we see that we extended the molecule by carbon-carbon chain, what reaction are you guys thinking of? What reaction extends the molecule by carbon-carbon bonds? Yeah, which increases the carbon-carbon length. Grignard reaction, right? Grignard reaction. Right, right. And what do you think this reactant will become in the Grignard reactant? a reaction? Would it be the Grignard reagent itself, or will it be the electrophile? Will it be the carbonyl that gets attacked, or will it become the MGBR nucleophile? Right, because from this final product here, this is the new bond that gets formed right there. That bond was not there before. That's the new bond that gets formed. Now we gotta figure out if this carbon here is gonna be the nucleophile or is it gonna be the electrophile in this reaction. Oh wait, to figure that out, to help us figure that out, let's go backwards. Retrosynthesis now. That's the going forwards part, right? We start off by going forward. Now let's go backwards. We know this is an ether here. What reaction do you guys know that could create an ether? What is one of the reactions we went over that creates an ether? Let's go backwards. So this is how you should think for these synthesis films. Go forward, go backwards, whichever one is easier first, and then try to meet in the middle later on, right? I just realized that I forgot to go backwards for this for you guys. So what reaction? Yeah, Williamson ether synthesis. And what was the reactant for Williamson ether synthesis? Like what functional group did we start up with for Williamson ether synthesis? Right, the product is an ether. What alcohol to ether, right? So this ether here will come from an alcohol. So let's go backwards. Going backwards here, say everything else stays the same. Whoa. Right, where this alcohol here is now this ether here. What reagents will we need to use to convert this alcohol to an ether? What is the first reaction? There's two reactions for Williamson ether synthesis. What was the first thing that happened? Acid-base reaction. That's right. How did you know where to attach the alcohol and where did it come from? Right. So for retrosynthetic analysis, right, in the product, I see that we have an ether functional group. R, O, R. Everything else are just regular alkanes, right? So when I go backwards here, I ask myself, what reaction do I know that makes an ether, which is Williamson ether synthesis. And Williamson ether synthesis starts from an alcohol and it makes an ether, which is this ether here. And because this ether here is bonded to this carbon right here, I drew the alcohol coming off of the same carbon where the ether is going to be formed at. Right, this R group here, we're going to worry about that later. Right, we're just going backwards here. Right, don't worry about where it comes from yet. We're just going backwards on how we got from this ether, like how we got to this ether from this alcohol here. Yeah, right. Where the first step is an acid-base reaction, which we can use a strong base like NaH, which the H minus is going to grab that H and give that oxygen a minus charge, right? Now, once this oxygen is a minus charge, what reactant do we want to react it with to get this ether here? Right. Once we have the nucleophilic O minus, what reagent can we use to make this new bond here? Right. Like if this was a nucleophile, how can we make this carbon here electrophilic? How can we make this carbon have a partial positive charge that is going to be attacked by the O minus? Okay. What is the second step of Williamson ether synthesis? Yeah. CH3, CH2, MGBR. Right? Where this dot right here, wait, let me do that different color. This green dot right here, the electrophile, is going to be that green dot right there that gets attacked from this O minus that gets formed from the acid base. Great. So that's the last reaction. The Williamson ether synthesis. Okay, so Notice how I starred this carbon here of the ring? That's a star right there. This red dot right here is going to be the electrophile. This is the new bond that we are going to form, new bond, right? Now we can see it more clearly. Let's make it a cut right there. Do you think this part right here was the nucleophile or the electrophile of Grignard reaction? Was that the nucleophile or electrophile of Grignard reaction? Yeah, I should have done that first, retrosynthetic analysis, and then ask you that question. But now's the time to ask that question here. Is this the nucleophile part or the electrophile part of this Grignard reaction that would form this product here? Was this the MGBR or was that the electrophile? Great. So for Grignard reaction, you can say that this looks like the electrophile, where some kind of Grignard reagent attacked it, right? Where if you say this is the Grignard reagent, the alcohol would have to be there, and then this right here would be your Grignard reagent, MGBR, where that's the star right there, right? And I think you guys were thinking of this star attacking that carbon and kicking out the leaving group bromine, right? But there's a problem here. There's a problem because even though there's a partial negative charge on that carbon right there, that partial negative charge carbon is very basic. This alcohol is getting in the way, right? The alcohol is getting in the way. So that would not happen. This arrow here would not happen. This nucleophile would not attack that electrophile. There's something else getting in the way, right? So what would happen if this was a nucleophile would be that this nucleophile would deprotonate itself to give this structure here, which is an intramolecular acid base reaction, right? This carbon attached to Mg is very basic. If it sees a hydrogen, then it's going to deprotonate that first, before doing any other thing, right? So that's why this part here cannot be the electrophile, right? If we make a cut here, whenever you see an alcohol, right, that's a big sign of where the electrophile came from. If you see an alcohol, that is this part here is going to be the electrophile that gets attacked, right? Which makes this part is a nucleophile, right? And to make this reagent into a Grignard reagent, we do magnesium. And you could put this solvent here, ether, to create this MGBR, which would give this carbon now a partial negative charge, right? Now, the electrophile that we said earlier with that dot came from a carbonyl. Its R group is right there. We could just bring this in as a reactant, and that would be a aldehyde because there is a invisible hydrogen right here, which I'm drawing out explicitly right here, right? Now this would work because first step, second step, H3O plus. When the negative charge carbon here attacks that carbonyl, we could pop that double bond onto the oxygen right there to give that oxygen an O minus charge, right? Which gets protonated by the H2O plus to become OH right there. So this was a little weird one because you're used to seeing Grignard reagents like being represented as the arrow, right? Or what are you guys used to seeing? Are you guys used to seeing the MGBR on the arrow, or are you guys used to seeing MGBR on the reactant? Whenever you guys did these Grignard reaction problems. On the arrow, right. So that's why this was confusing. For Levens, Helix, Nasiri, right? They can interchange them. Like they can interconvert them. They could put the Grignard reagent on the reactant and then the electrophile on the arrow. Has Ling give you guys an example problem where a Grignard was on the reactant before, or he's shown you only the Grignard reagent on the arrow? I see. Yeah. So it does not have to only come from the arrow. It can also come from the reactant here. And the arrow could be the electric. Because doing this is the exact same thing as saying this. Right? This is the same thing as saying that, which is the same thing as saying this. Right? These are the reactants, which could like be represented as this or this right here on the synthesis. So it just depends on what the synthesis reactant gives you, and that's how you tell if it's going to be the nucleophile or electrophile, depending on what the product is. How did you determine exactly which molecule would be able to attack MGBR successfully to get the alcohol? Right, so this right here, I determined that this was our electrophile because I see that on the reactant here, like from this alcohol, this is the new bond that gets formed between the original molecule we had, which is this cyclopentane with the methyl group, and this is the new group right here, right? And I know that this was a Grignard reaction because we added carbon-carbon bonds. We extended the chain carbon's length, right? So this carbon here, or this carbon here has to be the nucleophile or electrophile of the Grignard reaction, right? And I know that this part here was the electrophile because it has an alcohol, right? Which can come from this carbonyl here. When that Grignard reaction attacks that carbonyl and we pop the double bond onto the O minus, that O minus here would eventually become an alcohol from acid workup step, second step, acid workup step, right? So that's why I know that this right side here is the electrophile, which this dot carbon here attached to the alcohol was the carbonyl part, right? And then I just attached whatever is attached to that dot. That dot is attached to ethyl group, and a hydrogen. So that's how I figured out what this reagent is right there. I just brought it in. You could do that for synthesis. I think that's why you guys think this was a weird problem because it looks weird bringing in any kind of reagent you want here, right? You could do this. You could do this. Right. Nice. Any questions on this? Does this make sense? This overall synthesis round here? Right. So the first step that we did was halogenation or bromination specifically, because we want the more substituted carbon. The second reaction we did was Grignard reagent formation, right? We're forming the Grignard reagent, the MGBR. The third reaction we did was an actual Grignard reaction. And then this last one is Williamson ether synthesis, Wes. So that's what synthesis songs would look like moving forward, right? Multiple reactions like that. It could be 3, 4 steps, 5 steps, 6 steps. Yeah, no problem. Okay, speed run the rest of the final. Okay, let me know if something doesn't make sense, but I'm just gonna walk through this, talk to this without asking any questions. Okay. Okay. Right. So this question here is asking for RNS, right? He already highlighted the RNS for us. We want to do assign highest priority group, but before we do that, we gotta figure out where the lowest priority group is. The lowest priority group is on a dash, which is the hydrogen. So this is good. This is the first scenario that we went over. chlorine has the highest atomic number. This is gonna be 2, this is gonna be 3. Going this way is R, so that's R right there. Right, this is 2 because this carbon here is attached to chlorine, this carbon here is attached to 3 hydrogens. Right, this carbon center here, the lowest priority group is on a wedge, so this is the second scenario that we went over earlier. So we do everything normally, and then we flip at the end, right? There's a tie between this carbon, and this carbon. If there's a tie, we see what's attached to it, right? This carbon here is attached to a fluorine, carbon, and hydrogen. This carbon here is attached to an oxygen, carbon, and hydrogen. This carbon here is attached to hydrogen, hydrogen, hydrogen. Fluorine has the highest atomic number, so that's going to be number 1. This is going to be number 2. This is going to be number 3. Going this way, it looks R, right? But we got to flip it to S because the lowest priority group is on a wedge. So that's S right there. Right. Now, for this one here, this is not a chiral center because this group is the same group as that. So Na. Right. Okay. So next one, chiral or meso. So for these types of problems here, I like to convert it into the flat bond like this. So I'm going to number this 1, 2, 3, 4, 5, 6. Okay, this is the rotated version, but it doesn't matter how you number it. And let's say this is 1, 2, 3, 4, 5, 6. We see at 5 and 4, there's methyl groups. But at 5, there's a methyl group going down, so that's a dash. At 4, there's a methyl group going up, so that's a wedge. Right. So we said earlier that something like this is going to be chiral, right? Because this is a bond that cannot be rotated. There's 2 chiral centers here, no plane of symmetry, chiral. For this one right here, there's a chiral center here, no plane of symmetry. So get rid of that, chiral. Okay, so let's do this reaction. This gets protonated, boom, and then this becomes boom, 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 OH2 plus. We converted a bad leaving group into a good leaving group. And then this is primary, so the Br minus that got kicked out is going to come back, attack that carbon, kick out the leaving group, and get to this final product here with water. SN1 reaction involving the protonated alcohol as a substrate, SN2 reaction. So not E2, not E1, we didn't form double bonds there. Not SN1 because this forms a carbocation. SN1 forms a carbocation. No carbocation was formed in this mechanism, so get rid of that. SN2 reaction was formed because this bromine here attacked that substrate and kick out the leaving group at the same time. SN2. Nucleophile attack electrophile, kick out the leaving group at the same time. Right, but we couldn't do that originally because we didn't have a Br minus, and this is a bad leaving group. We had to convert that bad leaving group into a good leaving group first, and then do that attack. Right. Okay. So this one, a reaction can be performed as performed below. Please match the. Oh, we did this already. Nice, nice. Okay. Yep. Yep. So we did this already too. So yeah. Whenever you do this, right, put the answer on the box. So then, yeah, the TA can grade it, right? But yeah, this should be up here as the answer. And then the fragments we said there was a carbonyl from the IR 1700 range, which you could represent as this. There's an aldehyde, right? And because you put the aldehyde right there already, this carbonyl is kind of redundant. This carbonyl is represented by the aldehyde. The carbonyl is represented by the aldehyde here already, so you don't have to include another fragment with the carbonyl. You could say that there is an ester somewhere to get partial credit for that ester as well. And then you could even, based on the HNMR, do the R group that is attached to that final product here, which is this R group right here, right, to get partial credit. And then combining the pieces together, you should get that. Okay, this one. A regular alkane right here will have like no functional group. And we said earlier that the only reaction it could do if it's not unstable is halogenation, right? But halogenation, we need light or heat, so no reaction. right? Because this is in cold conditions. This one right here, good leaving group, form the double bond, so E2 reaction. But this is a Hoffman because we formed the less stable one. And if this is Hoffman, then we gotta use a bulky base like LDA or turbotoxide. Right. For this one right here, this is our Grignard reagent. This is our electrophile. Attack the electrophile. Kick out the leaving group. Star, making the bond between the star and dot. That's neo. The dot is attached to two methyl groups, 1, 2. Let me make sure. Oh, so he put no reaction, this one. Unless with CUI. MgCl. Grignard reagent. And then CUI. Wait, MgCl, Grignard. What? Huh, wait. Grignard reaction reacting with secondary halo alkane. CL is weak. Oh, is that what he said? Like, if this was MgCl, it would not react, but if it was MgBr, would that go through? If it was MgBr? Oh, I see. Um, when a gradient reaction is about leadership of this pathway converting alkane into an alkane in 2 steps. Right. So the way I've learned this reaction is that this Grignard reagent here can react with a halocane RX. It can react with a carbonyl, either a ketone or aldehyde, or it can react with an epoxide. Right. So this was the first scenario that I learned it in, but I'm not sure why this is the answer. So yeah, I'm not too sure why. I would store that. Do you guys know why this is no reaction here? I've never seen this before.
So I'm actually looking through my notes and I saw another problem that's pretty similar. Like it was MgCl again. So I'm guessing it's because of the chlorine that
Mm,
hits it.
right. And if you did you see a practice problem where they used MgBr with a halocane and the reaction did go through?
Yeah, they use THF and H3O plus. And
Oh, okay. With MgBr and then it went through with the reaction?
yeah, and it was still a secondary.
Secondary halocane.
Yes.
Oh, that's interesting. Okay. Dang. I never seen that before. Learning something new. Right. So Cl minus, you could think of that as too weak to react. Right. MgBr, like if it was MgBr, you would get this as the answer. Yeah. Yeah. I don't think I have time to go over SN1 and SN2 reactions in detail after I go over this final, but I did go over that in the midterm 2 review session, which you could access that to my YouTube video. I'll post this like sometime. I don't know the exams like what time is the exam? Like 8 a.m. I think, but the SN1 and SN2 reactions will be on that video. Okay. Okay, so this reaction here we did earlier. We have a secondary alcohol. We have a primary alcohol. This is a ketone. This right here is an aldehyde, right? Because we stop at this aldehyde, CHO, we gotta use PCC. Can't use Jones. If you use Jones, you'd get this, which is not the answer. But if this showed up as the answer, which you could put on the exam, you'd use Jones if this was the answer that he gave you guys. Oh, the product, I mean. Right, carboxylic acid. Right, because this primary alcohol here, depending on what oxidizing agent you use, PCC or Jones, you get different things, aldehyde or carboxylic acid. Right. Okay, so next one, let's do the mechanism. Oxygen would get protonated by the HBr, kick that out, form this thing here. And now this ether reaction, think of it as SN1 reaction. We're an aqueous solution, so we gotta choose which leaving group is gonna leave. Is it gonna be this leaving group to form the secondary carbocation, like right after it leaves, or is it gonna be this leaving group that leaves to form a primary carbocation? Primary carbocation is so unstable, we don't want that. So we're gonna use that as the leaving group, and then we're gonna kick that out to form this alcohol and this carbocation that gets formed after it lost the bond, where the Br minus is gonna come in to attack that carbocation to get that product right there. But you still have to include this as the answer because that's organic, right? That leaving group is organic. There's carbons and hydrogens there. So the answer here, let me double check. Is that right? Yep. Oh wait, it's the other way around. Wait, so it's not. Yeah, so it's not gonna be this. No. It is gonna be Br and OH. Okay, so the first step is right. We protonate the oxygen to get the O plus. Let's see what happens next. Okay, so now you can think of this as SN2 reaction now. Different professors do different things on this because whenever Levens and Nassiri what goes over this ether reaction stuff, I think Levens was like tertiary is the one that reacts first, and then primary, and then secondary is the least reactive one, right? Meaning that if you look at this OH right here, this is a primary carbon, this is a secondary carbon. In Levens' list, primary beats secondary, right? But according to Ling, oh wait, no, it's still the same list. Yeah, same list. Right. Primary beats secondary. Right, secondary is gonna be the least reactive one. So when the O attacks the H and kicks out the Br, right? This Br minus right here is now gonna choose between a primary carbon or a secondary carbon to attack. A primary carbon is gonna come from an SN2 reaction. Tertiary carbon is gonna do SN1 reaction. Secondary SN2. Right, there's no tertiary carbon here, so we don't do SN1. We're gonna do SN2. This bromine here is gonna attack that carbon, and then we're gonna kick out this leaving group right here. Kick that out. Right, and that's gonna give us these right here. Right, this product where the bromine attacked that carbon, and then this leaving group that left right there. Right, so keep in mind of this list right here: tertiary, primary, secondary for ether plus HX reaction, where X can be chlorine, bromine, or iodine. Right. The first step is to protonate the most basic atom to make that into OH plus. Then you gotta compare the carbons attached to that oxygen. Right. This carbon here is primary on the left side. This carbon here is secondary on the right side. And then looking at the list, primary beats secondary. So that's where the bromine is going to select for to attack, and then kick out to get the right answer. There, nice. We went over this earlier. Na, whenever you see that, is always a positive charge. H is always a negative charge. H minus is a very strong base because it's very unstable, very reactive. It's gonna look for the most basic hydrogen, acidic hydrogen, which is the alcohol hydrogen, and then that bond between oxygen and hydrogen is gonna break and give that oxygen a negative charge right there, right? Where Na plus is gonna float around that negative charge, and then H2 gas is gonna get formed as well. But this is optional. This is optional because they're not organic. This is the organic product that you need to draw in. Right. Okay. NaBH4 is a reducing agent, which reduces carbonyls. There's no carbonyl here, no reaction. Oh, epoxide now. Okay. So what is epoxide reaction? Think of this as a Grignard reagent. Whatever is attached to the Mg is negatively charged. Right. Now we have two electrophiles for this epoxide, and they're equally substituted, so we don't have to worry about which one's more substituted, which one's less substituted. But if it was asymmetrical, the Grignard reaction will always detect the less substituted side of the epoxide, right? Less substituted side of the epoxide. But this does not matter. So we're gonna have that star attack that dot. We're gonna pop this bond onto that oxygen right there. We're gonna break that bond and give that oxygen a negative charge. Right after that reaction, we're gonna have this star have a bond to this dot right here. And that's the new bond that got formed from that attack. Right. The MGBR dissolves. The dot here, let me say dot A, dot B. Dot A is still bonded to dot B. Right, I just say B right there, which is bonded to O minus. Right. This bond right here to the oxygen is that bond right there. But that oxygen now has a negative charge because it's no longer bonded to A. Right. That bond broke off and went onto that oxygen right there to give it O minus. Right. Now we bring in the second step, H3O plus, to protonate the O minus to get our final answer. So you could write it in this form, but that's kind of ugly, or you could redraw it into the regular bond line form like this: 1, 2, 3, 1, 2, 3, OH, like that. Right. So that's the mechanism of this Grignard reaction reacting with an epoxide. Okay, next one. Nomenclature. Okay, so let's figure out the longest chain. It could be 1, 2, 3, 4, 5, 6, or it could be 1, 2, 3, 4, 5, 6. Both are 6 carbons long. Both have its first substituent at carbon 3. There's no higher priority group here. Chlorine, and then that's when we do alphabetical order. C comes before ethyl, A, B, C, D, E. Yeah. So 3 chloro, 4 ethyl hexane. Right. If there's a tie between the two numbering systems, and the two groups here do not take priority, then that's when you look at alphabetical order. Which one comes first? C comes before E, so we're gonna use the red route. 1, 2, 3, 4, 5, 6. Now alcohol here is the highest priority group on a cyclopentane. So the base name is cyclopentanol, where our number 1 is going to be on that carbon right there with alcohol. 1, 2, 3, 4, 5. And then this methyl here is the substituent. So this is 1-methyl cyclopentanol. For this one here, I see alcohol, automatic high priority group. So that's going to be 1, 2, 3, 4, 5. This is not 6. That's not going to give us our longest chain, right? We're going to go up 6, 7. That's the longest chain, heptane. I'm going to circle the substituents in blue: methyl, chlorine, methyl, and the alcohol right there, right? Because the alcohol is on carbon 2, our base name would be 2-heptanol, because our longest chain is 7 carbons, 2-heptanol, right? And then our substituents we have are 4-chloro and 3,5-dimethyl, right? And when we do alphabetical order, it's going to be the C and M that counts. It's not going to be the D in di. So this one is going to be 4-chloro, because C comes before M. 3,5-dimethyl, 2-heptanol, right? Or you could have said like dimethyl heptane 2-O. Either one of those would be the same thing, right? Okay, this one here, 1, 2, 3, 4, 5, 6, 7, 8. This is 1. This is 2. This is 3. This is R. This is 1. Let's see. This is R. This is S. Okay, so this is going to be 2R, 4R, 6S, 2, 4, 6 trichloro octane. Okay, so this one is asking you to draw the condensed formula, left to right. CH3 is the CH3 part right here. CH, Cl, and then this part is CH because there's only one hydrogen there. This one is C, and then the substitute methyl group is going to be in parentheses, CH3. And then this ester here, you see an ester, the condensed formula is going to have a COO, right? And then the R group of the ester. So it's going to be COOCH3. Right. Now for this benzene ring here, we see another ester, right? We're not doing condensed formula. They're asking for the molecular formula. So just got the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. C9. Hydrogens. 1, 2, 3, 4, 5, 6, 7. 7 hydrogens. H7. 3 fluorines and 2 oxygens. Okay. Okay. Did that. Did that. Okay. Synthesis. Step by step at appropriate conditions, right? Answer in the box. C6. So whenever you see C6 or C whatever, this is your carbon limit, C limit. So that's the max amount of carbons you can use as the reactant in the reactant, right? And they want you to create this product here. So let me just put that product right here, right? And then we said earlier that when we see an alcohol with new R groups, right? Alcohol with new R groups, we could say that this came from a Grignard reaction, right? Where the alcohol was a carbonyl, right? Because when the Grignard attacks the carbonyl, that carbonyl gets popped up onto the O minus, which gets protonated to OH, alcohol, right? So we see 6 carbons here already, which we could say that that's our starting material. And we could say that this alcohol here, like we said earlier, came from a carbonyl. We could say that that carbonyl was right there. And this is still 6 carbons. 1, 2, 3, 4, 5, 6. Right? And because this is the carbonyl here, that dot is the electrophile that gets attacked. This dot is the electrophile that gets attacked. Right? That means that this star right here is the nucleophile, the MGBR, which this is the new bond between the star and dot. And to make that happen, we do this Grignard reagent with the 2 carbons MGBR. Second step, H3O plus. Right. This alcohol here came from this carbonyl. This new R group here came from the new R group of the Grignard, where this is the star carbon right here. When a star carbon attacks the dot, pop the double bond to the oxygen to create this O minus. New bond between star and dot. MGBR dissolves away. The star is attached to one other carbon right there. Right. How do you know there's a stereocenter? Oh, for this question here with the nomenclature, I knew there was a stereocenter because all of the groups that I said were stereocenters had 4 different unique groups attached to it. Right. Like this right here, chiral center, chiral center, chiral center. Chlorine, methyl, this whole group is one, and then that hydrogen is another one. 4 different unique groups. That's a stereocenter, a chiral center. Right. If there's 4 unique groups attached to that carbon. Okay, so C4 to this group right here. Okay, so let me try doing this without looking at the key first to show you my thought process on this. We start with 4 carbons. We have 1, 2, 3, 4. This is symmetrical. Nope. Let's see. Boom, boom, boom. 4. Okay. Do that. No. Let's see. So this final answer here is just alkanes. There's no oxygens, so it does not come from a carbonyl. 1, 2, 3, 4, 5, 6, 7, 8. 2 methyl groups and carbons 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Symmetrical. See what's going on here. Let me try to figure this out. Okay. Let's see. C4. Boom, 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 boom. Is this 4? 1, 2, 3, 4. Oh no, but we don't want oxygens there because we don't have any alcohols. Br, Br. Let's say these are the electrophiles, which are these dots right here. And then let's say that these are the new R groups. Right. And then we're gonna say 2 equivalent or excess amount of 1, 2, 3 mgbr. It has to be the Br, not the Cl, because Cl is too weak. Oh, and that's it. Which would give you boom, 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 boom. This is the star right here, which is the star and the star because we have 2 equivalents of them. And then these are the dots right here that gets attacked. And these are the new bonds that gets formed between them. That was kind of weird because we used 2 equivalents of the Grignard reagents and we were restricted to 4 carbons. But let me see what he did in his key. Okay, what he did was he started with this 4 carbon chain with 2 ketones, a diketone. And then he did 2 equivalents of 1, 2, 3 mgbr, same thing here. And then once you do that, right, this is the star because that's the carbon attached to the Mg. These are the dots. Right, I'm just going to show the mechanism once for 1 carbonyl. That star is going to attack the dot, and then the double bond is going to become an O minus. The second step here should have an acid workup step, H3O plus, before the PBr3, right? Because once that happens, this dot right here is now bonded to this star right here, which is bonded to 2 other carbons, 1, 2. And then the dot is now bonded to an O minus because we popped that double bond onto the O right there, which gives us that O minus, right? And then the H3O plus will clean it up, acid workup, to proton that O minus into an OH, right? But we do that again because we have 2 equivalents of it. So when we do that again, we should get this. 1, 2, 3. OH, 1, 2, 3. And PBr3. And then he put PBr3 to convert those alcohols into bromines right here. And then he reduced these bromines down to alkane. I've never seen that happen before. LiAlH4. Did you guys learn about this reaction where you could like just get rid of these halalkanes with the LiAlH4? I never seen this reaction happen before. It's weird. Because he started with the diketone, and then he had the alcohol, which got converted to the bromines, and then he reduced these bromines. He got rid of the bromines by LiH4, but I've never seen that reaction happen before. Is that in your notes, or like what reaction name is that? I'm not sure. Like what this is here. what's going on here. Oh, LILH4 can reduce halocanes to alkanes. That's interesting. What the heck? Right. With THF or yeah. So for synthesis problems, right? You don't have to include the solvent like THF or ether, right? If you just put the main reagent that does the reaction, like LiLH4, then you get full credit for synthesis, right? Those are just solvents that are there that facilitates the reaction. That would not interfere with the reaction, right? So alcohol is a bad leaving group, but it can get converted to any halogen using one of these reagents here, right? If we have any kind of alcohol and we use SOCO2, PBr3, or PI5, we could convert that alcohol into any of these halogens using those weird reagents. Right. Okay, so dang, there's new things that I'm learning. This thing was new to me, and then the MgCl 2 week to react is new to me. Okay, that's good. That's good. I didn't know that. Okay, but this would work as well. Where we start with this 4 carbon, 2 halocanes, and we use 2 equivalents of the MgBr, not the MgCl, because that's too weak to react. To react with these 2 leaving groups, kick that out and get this thing here. That would still work. Okay, mechanism. And then we're done. Let's see, mechanism for this one. Okay, so this is, oh, he went over this already. This is a 118B thing. That's good, that's good. This is dehydration. This is a good segue to 118B. So whenever you see acid, strong acid, look for the most basic atom. Our most basic atom here is this oxygen. This oxygen here is going to get protonated by the strong acid. Right, so that OH will grab the H from the H2SO4 and then kick out an HSO4 minus. Right. And then once we protonated that OH, we converted a bad leaving group into a good leaving group. Right, and because we're in heat conditions, we're gonna think of this as an E1-like reaction. E1-like reaction where heat makes the E1 product major. And we're in high heat here, 140 degrees Celsius. Right? And the first step of this reaction is that the leaving group will leave to form this carbocation. And then whenever we form this carbocation here, we always have to look out for a rearrangement step, either hydride shift or metal shift. But in this case, we don't have to worry about that because it's already at its most stable position here. Right? And then from there, since we want to do E1, look at a beta hydrogen. It doesn't matter which one, they're symmetrical. And then use the conjugate base, HSO4 minus, to grab that beta hydrogen and make a double bond right there. To get that final product right there. Right. You could use that, or you could use what he said, water. But the reason why I didn't use water was because there was no water included in the reagent here. Right. Yeah, but he allows you to use water, so you can use water in this case here. Okay. Yeah, these are reversible. Okay. Last one. So whenever you see K, think of it as Na, right? Na or K, they are associated with a positive charge, right? So since this K has a positive charge, this H will have a negative charge, right? And this H with a negative charge right here is a strong base, right? And because it's a strong base, it's going to look for the most acidic hydrogen. The most acidic hydrogen is this hydrogen here attached to the most electronegative atom oxygen. So the acid-base reaction is one of the fastest reactions in OChem you have alongside with intramolecular reactions. So when we deprotonate that alcohol, we're going to create this alkoxide ion, the negative charge on the oxygen, right? Which is our nucleophile here. And our electrophile is this positive charge carbon right here. if the nucleophile and electrophile are in the same molecule, this type of reaction is specifically called an intramolecular reaction, right? And all intramolecular reactions will always form a ring. So this O minus here is going to attack that carbon and kick out this leaving group. And for intramolecular reactions, I like to number them from the attacking atom, 1, and I go all the way to the atom being attacked. 1, 2, 3, 4, 5. So I know that we're going to make a 5-membered ring, right? And the 5-membered ring that we're going to form has oxygen as the first atom. So let's draw oxygen there and draw the 5-membered ring like that, right? And then this is 1, 2, 3, 4, 5. There was nothing attached to 3 or 4, like there's no methyl group there, so we don't have to include methyl groups there. But if there were methyl groups there, that's why you number them, to keep track of all the groups. Like if there's a methyl group here, isopropyl group here, you put the methyl group at carbon 3, isopropyl group at carbon 4, to keep track of everything. But in this case, there's no groups, so don't worry about that. So that's the final answer there. And if this is mechanism, Br minus that left, left as a Br minus as well. Yeah. What else do we need for the actual answer for this last one? So for this last one right here, Levens wants you to put the Br minus because that's what actually leaves. But for Ling's test, he leaves it as optional. He just puts the organic products. In this case, no water was formed, but H2 gas was formed. And the H2 gas that gets formed was from this H minus grabbing that H right there, becoming H2 gas. Right? Water is not formed in this reaction. Oh, so the K right here is still around. The K is going to float around the bromine minus now. It's a spectator ion. Right? You know when an intermolecular will happen if the nucleophile is on the same molecule as the electrophile. So you could think of it as the molecule attacking itself. Molecule attacks itself. And when it attacks itself, it always forms a ring. Right? We see this nucleophile here attacks itself. Like this whole molecule is attacking itself, forming a ring. Did that make sense? How do you find the electrophile? Yeah. So the electrophile is going to be the atom that's positive charge. This atom here is positively charged because it's attached to this electronegative bromine that's pulling on the carbon's electrons. If it's pulling on the carbon's electrons, the electronegative atom is partial negative charge. This carbon here is partial positive charge, making that the electrophile. Right, so electrophile is positive, nucleophile negative. Nucleophile always attacks the electrophile, not the other way around. Yeah, did that make sense? Yeah, no problem. Okay, do you guys want to take a group picture for my my Instagram that I'm gonna post tomorrow for my private tutees on Zoom? Isn't the second carbon in that same chain also partial positive since it's bonded with oxygen? Yes, this oxygen here is also partial positive, right? But that's not going to be the electrophile because there's no good leaving group. There's no good leaving group to kick out. And then this O minus here, when it attacks itself, it's impossible to form a 2-membered ring. We cannot form a 2-membered ring here, so that's why that's not going to be the electrophile. Also, this electrophile here has no good leaving group to kick out when it gets attacked. This one here, right, it does have a good leaving group to kick out, and it could form a stable ring, a 5-membered ring, 6-membered ring. Are the reactions to watch out for other reactions that is based on different temperature, like number 10. So temperature for 118A, just think of it as E1, right? You'll learn more about temperature stuff in 118B, but the temperature for 118A is E1 like for dehydration for temperature. So for 118A, that's it. You need to worry about. This recording will be posted as soon as the recording is sent on Zoom for me, which is like probably later. What time is your exam? What time are your guys' exams? 8 a.m. Oh shoot. Oh my god. So it might not be posted until like, I don't know, like because like I don't know. That's kind of too late because I'll try my best. I'll post it in the Discord though. Like if I like wake up in the middle of the night for some reason, I'll post it and send it to Discord and my YouTube channel as well. Yeah. Do you guys want to take a quick group picture for my Instagram that I'm gonna post tomorrow? Wait, Okay. Or shoot, or are you guys uncomfortable with like sharing your camera, or like if you guys are comfortable sharing camera, let's take a quick share. Okay. Okay. Good luck with your final coming up on tomorrow 8 a.m. Are you guys planning to go sleep now or study a little bit more? Are you guys pulling on others? Are you guys what are you guys planning to do now? Pray? Oh, neither. Study more. Yeah. Write your note card. Take a power nap. Yeah. Power nap and then go back to studying. Oh my god. Okay. Well, if I'm up by then, if you guys are still up by then, I'll send the recording for you guys to go back and watch. Well, other than that, good luck, and I will let you guys go study now. Yeah, no problem. Mhm. Yeah. Bye. No problem.